What if I told you that the universe is hiding an invisible secret, one so vast that it outweighs everything we can actually see? That's the enigma of dark matter, the mysterious substance making up nearly 85% of all matter in the cosmos. For decades, scientists have been chasing shadows, trying to pin down what this elusive stuff really is. And here's where things get even more intriguing. Among the countless theories, one tiny, hypothetical particle called the axion has emerged as a leading contender. It's a ghostly whisper in the dark, a particle so light it could slip through your hand unnoticed, yet it might hold the key to unlocking the universe's greatest mystery. Now imagine this, axions aren't just some far-fetched idea. They were first dreamed up to solve a puzzle in particle physics, but today they're at the heart of 40 startling theories about dark matter. Some suggest axions could be freezing cold, drifting through space like an unseen ocean. Others propose they're born from the chaos of the early universe, relics of a time when everything was hotter and denser than we can fathom. And then there are the wilder ideas like axions forming invisible rivers that shape galaxies, or even creating bizarre, ghostly stars made entirely of dark matter. The possibilities are as vast as they are mind-bending. This isn't just about filling in a gap in our textbooks. If axions are real, they could rewrite the story of the cosmos and our place in it. Think about that for a second. We might be standing on the brink of a discovery that changes how we see everything. So buckle up, because today we're diving deep into these 40 theories, unraveling the science, the mysteries, and the sheer wonder of what axions could mean. By the time we're done, you'll see the universe and its shadows in a whole new light. To understand why axions became a dark matter candidate, we have to rewind to the 1970s, a time when physics was wrestling with a puzzle so stubborn it threatened to unravel our understanding of the subatomic world. The problem was called the strong CP problem, and it had scientists scratching their heads. You see, according to quantum theory, the force that holds atomic nuclei together, the strong nuclear force should naturally allow for something called CP violation, where particles behave differently from their mirror image counterparts. But here's the kicker. In reality, that violation was nowhere to be found. The universe seemed weirdly symmetrical, and no one could explain why. Enter Peccei and Peccei-Quinn, two brilliant physicists who proposed an elegant solution. They suggested that nature might have a hidden symmetry, one that cancels out the effects of CP violation, making it appear as if it never existed. But like all great ideas in science, their theory came with a surprising twist. To make the math work, they needed a new particle, one that would act like a cosmic reset button, quietly restoring balance to the quantum world. That particle became known as the axion, named after a laundry detergent brand because, in theory, it cleaned up the messy problem. But here's where things get even more fascinating. The axion wasn't just a mathematical fix, it had real physical properties. It was predicted to be incredibly light, barely interacting with ordinary matter, and astonishingly stable. These traits made it a perfect candidate for something much bigger, dark matter. Think about it. If axions were abundant enough, drifting through space like an invisible mist, their collective mass could explain why galaxies spin faster than expected, or why light bends around seemingly empty patches of the cosmos. It was an accidental discovery with universe-shaking implications. So while Peccei and Quinn set out to solve a niche problem in particle physics, they might have inadvertently uncovered the ghostly building blocks of the cosmos itself. And that's the beauty of science. Sometimes the answers we find are far stranger and more magnificent than the questions we started with. The original axion theory was elegant, but like all good science, it didn't stay frozen in time. As our understanding of quantum field theory deepened, so did the axion story, and recent breakthroughs have reshaped it in ways Peccei and Quinn could never have imagined. Take the axion's mass, for example. Early estimates placed it somewhere between a trillionth and a billionth of an electron's mass, so tiny it seemed almost theoretical. But cosmological observations have tightened those bounds dramatically. We now know that if axions make up dark matter, their mass likely falls within a razor-thin window, heavier than a stray whisper but lighter than the faintest shadow. Then there's the puzzle of coupling constants, how strongly axions interact with other particles. Initially, theorists assumed these couplings were fixed by the math, but modern simulations tell a different story. When you factor in the chaos of the early universe, cosmic inflation, phase transitions, even the birth of primordial black holes, those couplings start to dance. Some models suggest axions could have wildly variable strengths in different corners of space, like a radio dial tuning itself across the cosmos. Others propose they might talk to dark photons, creating invisible force fields weaving through galaxies. What's truly astonishing is how these tweaks aren't just academic. They're reshaping real-world experiments. Teams hunting for axions are now designing detectors tuned to these refined predictions, from ultra-sensitive quantum cavities buried underground to telescopes scanning for telltale flickers in starlight. It's a Goldilocks scenario: too heavy and axions would have been spotted by now, too light and they'd fail to clump into the dark matter halos we observe. But right in that narrow sweet spot, that's where the magic might be hiding, a ghostly particle refined by the universe itself. Axions may be the star of the dark matter conversation, but they're not alone in this cosmic mystery. Enter their more flexible cousins, axion-like particles or ALP. Unlike the original axion born to solve the strong CP problem, ALPs aren't tied to any one theory. They're a broader class of particles, free to vary in mass and how they interact with other forces, making them a playground for theorists. Imagine axions as a single instrument in an orchestra, perfectly tuned for one role, while ALPs are the entire string section, capable of a symphony of possibilities. What makes ALPs so intriguing is their adaptability. Where the classic axions properties are locked in by quantum field theory, ALPs can be lighter, heavier, or even completely decoupled from the rules that bind their better-known relative. Some models suggest they could be billions of times lighter than electrons, drifting through space like quantum fog. Others propose they're just heavy enough to clump into dense, invisible structures, dark matter filaments weaving between galaxies. And their couplings, those could range from whisper-weak to just strong enough to leave faint traces in high-energy particle collisions. This flexibility isn't just theoretical convenience. ALPs solve problems the original axion can't. Take the missing satellite puzzle. Simulations predict our Milky Way should be surrounded by thousands of tiny dwarf galaxies, but we've only spotted a handful. If dark matter is made of ALPs with just the right mass, they could suppress the formation of these satellites, neatly filling the gap between theory and observation. Or consider black hole physics. Some ALP models predict they'd interact with intense magnetic fields around spinning black holes, producing bursts of detectable radiation. The hunt for ALPs has spawned some of the most creative experiments in modern physics. From repurposing MRI magnets to scan for their faint signals, to using neutron stars as natural particle accelerators, scientists are casting a wider net than ever. And here's the kicker: if ALPs exist, they might not just be dark matter. They could also explain anomalies like the inexplicable transparency of the universe to high-energy gamma rays, or even hints of unexpected light polarization from distant quasars. So while axions remain a compelling candidate, ALPs remind us that the universe seldom fits into neat boxes. The truth might be messier, wilder, and far more interesting than we've dared to imagine. And that's what makes this search so thrilling. Every unanswered question is an invitation to look deeper. String theory has always been a playground for the imagination, a place where the fabric of reality stretches far beyond the 4 dimensions we experience. But hidden within its equations lies something extraordinary, a potential answer to why action-like particles or ALP might be everywhere. Picture this: string theory suggests our universe isn't just 3 dimensions of space and 1 of time. Instead, it's woven from tiny, curled-up extra dimensions, compactified so tightly we'd never notice them. And here's the twist: when these dimensions vibrate and fold in on themselves, they could produce a cascade of ultralight particles, flooding the cosmos like an invisible mist. That mist, it's theorized to be LPs. Unlike the original peccei-quinn action, these particles wouldn't just solve a single physics problem. They'd emerge naturally from the geometry of the universe itself, their properties dictated by the shape and size of those hidden dimensions. Some models even suggest that because string theory allows for an almost infinite variety of compactified shapes, each with its own vibrational modes, it could spawn not just one type of LP but a whole spectrum. Imagine tuning a guitar with 100 extra strings. Every possible note would fill the air. Now replace those notes with particles, and you've got a universe humming with LPs of every conceivable mass and coupling strength. This isn't just abstract math. If string theory's LPs exist, they'd behave unlike anything in the standard model. Their sheer lightness, some billions of times lighter than electrons, would let them evade detection effortlessly, forming a kind of quantum fog that permeates every corner of space. But here's where it gets wild. This fog wouldn't be static. Because ALPs are so light, their quantum waves could stretch across entire galaxies, creating interference patterns on scales we're only beginning to probe. Some physicists speculate these waves might even imprint faint ripples on the cosmic microwave background, leaving fingerprints from the dawn of time. And then there's dark matter. If ALPs are as abundant as string theory suggests, their collective mass could explain why galaxies hold together the way they do. Unlike heavier particles which clump into dense halos, ultralight LPs would behave more like a fluid, flowing into vast, diffuse clouds that cradle galaxies without ever colliding. It's a radical departure from traditional dark matter candidates, one that could solve long-standing puzzles, like why some dwarf galaxies appear smoother and less clumpy than simulations predict. The real beauty of this idea: it's testable. While we might never see the extra dimensions directly, their influence could show up in subtle ways. Experiments like the Action Dark Matter E-experiment, or ADMX, are already tuning their detectors to listen for ALP's faint signals. Others are scanning the light from distant quasars, searching for telltale shifts caused by LPs interacting with magnetic fields in intergalactic space. Even black holes could be part of the story. Their intense gravity might convert LPs into detectable photons, creating bursts of energy that telescopes could spot. So while string theory's extra dimensions remain elusive, their echoes might already be all around us, woven into the fabric of dark matter itself. And if we're right, uncovering these whispers could be the first step toward a revolution, one that bridges the quantum world and the cosmos in ways we're only starting to dream of. Let's rewind the clock to the earliest moments of our universe, a time so hot and dense that particles didn't just move, they practically danced in a quantum frenzy. In this primordial soup, actions wouldn't have been the solitary, ghostly particles we imagine today. Instead, they'd have been born in a very specific way through a cosmic phenomenon called the misalignment mechanism. Here's how it works. Imagine the early universe as a vast, seething ocean of energy, where the laws of physics were still settling into place. In this chaos, actions weren't yet particles but rather a field, a kind of invisible scaffold stretching across space, vibrating at a frequency set by the universe's temperature. But as the cosmos expanded and cooled, something remarkable happened. This action field got stuck. Picture a ball rolling down a hill, only for the hill itself to suddenly flatten out, leaving the ball stranded halfway down. That's essentially what occurred. The action field couldn't relax to its lowest energy state because the universe was changing too fast. Instead, it froze in place, locked in a misaligned configuration. And here's the kicker: as the universe kept cooling, this trapped energy had to go somewhere. It couldn't just vanish. So, like water vapor condensing into dew, the action field fragmented into trillions upon trillions of individual particles, actions flooding the cosmos in an instant. Now, these actions weren't like ordinary matter. Because of their bizarre quantum properties, they wouldn't bump into each other or slow down. Instead, they'd all occupy the same lowest energy state, overlapping like waves in perfect sync. This is what physicists call a Bose-Einstein condensate, a single, coherent quantum entity spanning the entire universe. And if that sounds mind-bending, wait for the punchline. This condensate wouldn't just sit there. It would behave like a superfluid, flowing without friction, wrapping around galaxies like an invisible cloak. That's the eerie elegance of the misalignment mechanism. It turns the action field's mistake into the very fabric of dark matter. But how do we know this isn't just theoretical sleight of hand? The evidence might be hiding in plain sight. If actions formed this way, their collective mass would naturally align with the observed density of dark matter, no fine-tuning required. Even their distribution fits. Because they're so light, they'd avoid clumping too densely, explaining why dark matter halos around galaxies appear smoother than simulations predict for heavier particles. And here's where it gets even stranger. Some models suggest this action condensate could have left faint ripples in the cosmic microwave background, subtle wrinkles in the afterglow of the Big Bang that future telescopes might one day detect. So while the misalignment mechanism might sound like an abstract twist of quantum physics, it's anything but. It's a cosmic story of symmetry broken, energy trapped, and particles born from the universe's own growing pains. A story that might finally explain why the night sky is filled with shadows we can't see but can't ignore. The cosmic microwave background isn't just a snapshot of the universe's infancy, it's a treasure map, etched with faint whispers from a time before stars or galaxies even existed. And if we know how to read it, those whispers might just reveal the fingerprints of actions. Picture this: when the Planck satellite mapped the CMB in exquisite detail, it didn't just capture a uniform glow. Instead, it found subtle temperature variations, patches slightly warmer or cooler than average, like the brushstrokes of some cosmic artist. These anisotropies aren't random. They're the echoes of quantum fluctuations stretched across the sky by inflation, frozen in place when the universe was just 380,000 years old. But here's where actions enter the story. If the misalignment mechanism flooded the early cosmos with these particles, they wouldn't have stayed silent. Their quantum nature means they'd behave more like waves than particles, oscillating in sync across vast distances. These oscillations could have subtly tweaked the density of matter in the early universe, leaving imprints on how those CMB temperature variations are distributed. Think of it like dropping a pebble into a pond. The ripples wouldn't just spread outward. They'd interfere with one another, creating patterns that reflect the pebble's size and shape. In this case, the pebble is the action's mass, and the ripples are written in the CMB's anisotropy spectrum. Planck's data already holds tantalizing hints. Some of the CMB's large-scale patterns appear slightly smoother than standard cosmology, predicts almost as if something dampened the universe's early density fluctuations. Actions could explain this. Because they're so light, their wave-like nature would prevent them from clumping too tightly, subtly smoothing out the distribution of matter before it could imprint sharper features on the CMB. It's a tiny effect buried in the noise of the data, but it's precisely the kind of subtlety that future missions like the Simons Observatory or CMB S4 might finally tease out. And then there's polarization, the CMB's hidden language. When light from the early universe scattered off electrons, it didn't just carry temperature information. It also became polarized, its electric fields aligned in specific directions. Actions could have left their mark here too. If they interacted with photons in the primordial plasma, even weakly, they might have twisted that polarization in detectable ways. Some theories even suggest that certain anomalous patterns in Planck's polarization, data features that don't quite fit the standard model, could be the ghostly handshake between actions and light. Of course, the CMB isn't handing us answers on a silver platter. These signals are buried under layers of cosmic noise, and teasing them out requires painstaking statistical analysis. But that's what makes this search so thrilling. Every anomaly, every slight deviation from expectation could be a clue, a fragment of evidence pointing toward actions woven into the universe's oldest light. And if we're right, the CMB isn't just a relic of the past, it's a message waiting to be decoded. Imagine a galaxy where dark matter doesn't just lurk invisibly in the background, but gathers into strange, shimmering structures like ghostly versions of stars and planets. That's the wild possibility posed by axion miniclusters and axion stars. Unlike traditional dark matter particles which drift diffusely, action's unique quantum properties could let them clump into objects ranging from asteroid-sized blobs to sprawling, star-like orbs. How it all comes down to gravity and a bizarre quantum quirk called Bose-Einstein condensation. Picture the early universe again, moments after actions formed through the misalignment mechanism. While most would spread smoothly across space, tiny density fluctuations, leftover wrinkles from cosmic inflation, could have caused some regions to become ever so slightly denser. Over billions of years, gravity would amplify these imperfections, pulling actions together. But here's the twist: because actions are ultra-light and behave like waves, they wouldn't just collapse into compact balls. Instead, they'd form vast, fuzzy halos called miniclusters, some as massive as Earth, others rivaling entire solar systems. These wouldn't be solid objects, but rather swirling, wave-like structures, their boundaries blurred by quantum uncertainty. At the smaller end of the spectrum, something even stranger could emerge: axion stars. Think of these as the dark matter equivalent of neutron stars, incredibly dense, but built from quantum waves instead of matter. If enough actions gathered in one place, their mutual gravity could overcome the natural pressure of their wave-like motion, causing them to condense into a stable, self-gravitating object. The result: a star with no nuclear fusion, no light, just a glowing mass of actions held together by their own ghostly pull. Some theories suggest these stars could span kilometers across, yet weigh less than a small moon, their density so low you could pass a spaceship right through one without noticing. But how would we ever detect something so intangible? The answer lies in gravity's fingerprints. Just like ordinary stars, axion miniclusters and stars would bend light passing near them, an effect called gravitational lensing. Telescopes scanning the night sky have already spotted mysterious microlensing events where distant stars flicker unexpectedly, their light warped by unseen masses. While most explanations point to rogue planets or black holes, some of these anomalies could be axion structures drifting silently through our galaxy. Even more intriguing, certain axion stars might not stay dark forever. If their density reaches a critical threshold, quantum effects could trigger a dramatic collapse, converting actions into bursts of detectable photons. Some astrophysicists speculate that rare, unexplained radio flashes like the infamous WOW signal could be the death cries of these exotic objects. Others propose that colliding axion stars might ripple spacetime itself, producing gravitational waves subtle enough to evade current detectors but within reach of future observatories. The hunt for these phantoms is already underway. Teams are scouring archival lensing data for patterns that don't fit conventional astrophysics, while others model how axion structures would distort the cosmic microwave background. It's a needle in a haystack challenge, but if we succeed, the payoff would be staggering: not just proof of actions, but a whole new class of celestial objects, invisible yet shaping the cosmos in ways we're only beginning to dream of. One of the most astonishing things about actions is how something so ghostly could leave a visible trace in our world, and it all comes down to their ability to talk to light. This isn't science fiction. It's a phenomenon called axion-photon coupling, where these elusive particles can temporarily morph into photons under the right conditions. Picture an axion drifting through a magnetic field, its quantum nature flickering like a candle in the wind. If the field is strong enough, the axion might transform, just for an instant, into a particle of light. This fleeting conversion is our best shot at catching dark matter red-handed. But how does this two-photon interaction actually work? At the quantum level, axions couple to photons through a process mediated by virtual particles, a kind of subatomic handshake where energy and momentum are exchanged. It's similar to how a prism splits white light into colors, except here the axion's energy dictates the photon's frequency. The stronger the magnetic field, the higher the chance this swap occurs. This rare but predictable behavior is the backbone of experiments like ADMX, the Axion Dark Matter experiment, which hunts for axions by turning them into detectable microwaves. Imagine a high-tech radio receiver tuned to the universe's quietest station, listening for the faintest whisper of a converted axion. Solar axion searches take this idea even further. The Sun, a cauldron of nuclear reactions, could be churning out axions alongside its usual light and heat. If these solar axions reach Earth and pass through a powerful magnetic field, like those in detectors such as CERN-CAST, they might reveal themselves as unexpected X-rays. It's like turning the Sun into a cosmic flashlight, illuminating particles we'd otherwise never see. What's truly remarkable is how these experiments exploit the axion's shyness. Its weak coupling means false signals are rare, making any detection a potential game-changer. And if we succeed, we'll have done more than proven a theory. We'll have opened a window into the quantum shadows where dark matter hides. From the quiet tunnels of particle physics labs to the high-stakes world of dark matter hunting, one experiment stands out as a potential game-changer: the dielectric haloscope. Unlike traditional detectors that scan one frequency at a time, this bold new approach aims to cast a wider net, searching for axions across a broad spectrum with unprecedented precision. The idea is as elegant as it is ingenious. Stack multiple layers of precisely tuned dielectric materials inside a powerful magnetic field, creating a kind of light amplifier for axion conversions. Here's how it works. When an axion passes through this layered structure, each dielectric boundary acts like a tiny mirror, reflecting the photon it converts into. These reflections add up constructively like ripples merging into a wave, boosting the signal until it becomes detectable. The beauty of this design lies in its scalability. By adjusting the spacing between layers, researchers can tune the haloscope to different axion masses, effectively turning one device into a versatile dark matter scanner. This is the core innovation behind MadMax, a collaboration pushing the boundaries of axion detection with a setup so sensitive it could spot an axion conversion in a sea of cosmic noise. What makes MadMax particularly thrilling is its potential to probe axions in a mass range other experiments simply can't reach. While ADMX focuses on lighter axions, MadMax targets those slightly heavier, up to a few dozen microelectronvolts, filling a critical gap in the search. Imagine combing through a forest with two different sieves. One catches the smallest leaves, the other grabs the slightly larger twigs. Together, they cover ground faster and more thoroughly than either could alone. But building a dielectric haloscope isn't without its challenges. The materials must be near perfect to minimize photon absorption, and the magnetic fields required are intense, so strong that only cutting-edge superconducting magnets can generate them. Then there's the issue of thermal noise. Even at cryogenic temperatures, stray heat can drown out faint signals, demanding cooling systems that push engineering limits. Yet despite these hurdles, the first prototype tests have been promising, and if MadMax succeeds, it could deliver something no other experiment has: definitive proof that axions are real. The implications stretch far beyond dark matter. A detection would confirm not just the existence of actions but also validate decades of theoretical work in quantum field theory. It might even open doors to new technologies. Imagine harnessing axion-photon conversions for next-generation quantum sensors or ultra-secure communication. For now, though, all eyes are on the teams fine-tuning their dielectric stacks, waiting for the day when the universe finally whispers back. Neutron stars are already cosmic oddities, collapsed stellar cores so dense that a teaspoon of their material would weigh 1 billion tons. But what if these extreme objects are also nature's perfect action detectors? That's the bold idea behind the axion dark matter radio hypothesis. Picture this: a neutron star's magnetic field is trillions of times stronger than Earth's, twisting space-time itself into a frenzy. If axions drift into this maelstrom, their interactions with the magnetic field could trigger a remarkable transformation, converting directly into radio waves. It's like turning the entire neutron star into a celestial transmitter, broadcasting signals we might pick up right here on Earth. This isn't just theoretical guesswork. The math reveals something extraordinary. Axions passing through a neutron star's magnetosphere would gain energy from the star's immense gravity, much like a roller coaster accelerating downhill. At a critical point, quantum effects kick in and the axions decay into pairs of photons, predominantly in the radio frequency range. The result, a narrow, persistent signal emanating from the star, its frequency determined by the axion's mass. Unlike sporadic astrophysical bursts, this emission would be steady and monochromatic, a pure tone ringing across the cosmos. Projects like Organ in Australia and Torad in the Netherlands are pioneering the search for these faint cosmic whispers. Organ, the oscillating resonant group axion experiment, uses a high-Q cavity, essentially a super-sensitive radio receiver, tuned to specific frequencies where axion conversions might occur. Meanwhile, Torad takes a different approach, repurposing radio telescopes to scan neutron stars for anomalous emissions. Both strategies face the same daunting challenge: isolating a needle of axion-converted radio waves in a haystack of cosmic noise. What makes these efforts so compelling is their potential to bypass the limitations of traditional lab experiments. Neutron stars offer magnetic fields and gravitational intensities no Earth-based machine could replicate, amplifying the chances of spotting elusive axion interactions. If successful, we wouldn't just confirm axions as dark matter, we'd unlock a new way to study the universe, using neutron stars as natural particle physics labs. And the implications go even further. If axions are out there, their radio signals could carry encoded details about the neutron stars themselves, revealing secrets about magnetic field dynamics or even exotic states of matter in their cores. So while these projects might sound like science fiction, they're grounded in cutting-edge physics. Every scan of a neutron star's radio profile brings us closer to answering one of cosmology's biggest questions, and tuning into a frequency that might rewrite the story of dark matter. Black holes aren't just cosmic vacuum cleaners, they're also some of the universe's most powerful particle accelerators. And when it comes to axions, their intense gravity might be doing something extraordinary, acting like a quantum amplifier, turning faint axion waves into detectable signals. This bizarre phenomenon is called black hole superradiance, and it could be our best shot at spotting axions without ever building a detector. Here's how it works. Imagine a spinning black hole, its gravity so strong it twists space-time around it like water circling a drain. If axions exist, their wave-like nature means they can't just fall in. Instead, they get caught in orbit, forming what physicists call a gravitational atom, a cloud of axions bound to the black hole's pull, much like electrons around a nucleus. But this isn't a stable partnership. The black hole's rotation injects energy into the axion cloud, causing it to grow denser and more organized over time. Think of it like pushing a swing at just the right moment. Each nudge adds energy, making the swing go higher. In this case, the black hole's spin, pushes the action field, amplifying it until the cloud reaches staggering proportions. Some models suggest these clouds could grow to be thousands of times wider than the black hole itself, humming with coherent action waves. And here's where it gets wild. As the cloud extracts energy from the black hole's rotation, the black hole actually slows down like a top, losing speed to friction. This energy transfer isn't silent. The oscillating action cloud emits gravitational waves, ripples in spacetime so precise they'd carry the action's fingerprint. Unlike the chaotic mergers LIGO usually detects, these waves would have a distinct, nearly monochromatic frequency determined by the action's mass. It's the difference between hearing a random crash and listening to a perfectly tuned violin note. Future interferometers like LISA or the Einstein telescope could spot these signals, potentially revealing actions indirectly through their gravitational echoes. The implications go even deeper. If superradiance happens, it wouldn't just prove actions exist, it would also give us a way to measure their mass. The frequency of the gravitational waves would directly correlate with the action's mass, turning the black hole action system into a cosmic scale. And because superradiance only works for certain mass ranges, a detection would narrow down action properties dramatically, ruling out whole swaths of theories at once. But the real magic lies in the scale. These action clouds could be vast, some spanning billions of kilometers, making them among the largest quantum objects in the universe. Their sheer size means they'd interact with passing gravitational waves in subtle ways, potentially imprinting secondary signatures on signals from colliding neutron stars or other black holes. It's a cascade of effects, each one a potential clue. So while we might not have definitive proof yet, the hunt is heating up. Teams are already scouring LIGO data for hints of these monochromatic waves, and theorists are refining models to predict exactly what to listen for. If black hole superradiance is real, it would mean the universe has been running its own action experiment all along, one where spacetime itself is the lab and gravity the detector. And we're just starting to tune in. Black holes and actions might seem like an unlikely pair, but under the right conditions, their dance could turn catastrophic, leading to one of the most explosive scenarios in theoretical physics, the black hole bomb. Picture this, a spinning black hole, its gravitational grip so intense it warps spacetime itself, surrounded by a swirling cloud of actions. Normally, this cloud would grow steadily through superradiance, siphoning energy from the black hole's rotation like a cosmic siphon. But if the actions interact just right, or perhaps just wrong, that steady growth could tip into a runaway reaction, culminating in a violent burst of gamma rays visible across the universe. Here's how the bomb mechanism works. As the action cloud extracts energy from the black hole, it doesn't just passively accumulate mass. Certain action models allow these particles to decay into pairs of photons when their density reaches a critical threshold. Now, imagine billions of actions packed into a quantum wave around the black hole, suddenly converting into high-energy gamma rays all at once. The result: a feedback loop where escaping photons trigger more action decays, releasing an avalanche of radiation in a matter of seconds. It's the astrophysical equivalent of a nuclear chain reaction, except fueled by dark matter and gravity instead of uranium. What makes this scenario so chillingly plausible is the math behind it. The black hole's rotation acts like a battery, storing immense energy in its spin. The action cloud, meanwhile, serves as both a capacitor and a detonator, storing that energy until quantum effects push it over the edge. Simulations show that under the right conditions, this process could release as much energy as a supernova packed into a tightly focused jet. And while we've never definitively observed such an event, there are tantalizing candidates. Some of the brightest gamma-ray bursts on record, like GRB 940229, have defied conventional explanations. Could these be the smoking guns of action-fed black hole bombs? The implications are staggering. If this phenomenon is real, it would mean black holes aren't just endpoints for matter. they're potential dark matter reactors capable of converting ghostly actions into some of the most energetic radiation in existence. It also raises a provocative question. Could these explosions leave behind forensic evidence? Theorists speculate that the aftermath might include distinctive X-ray afterglows or even gravitational wave signatures, subtle echoes of the explosion's birth. Yet for all its drama, the black hole bomb isn't just a doomsday scenario. It's also a potential goldmine for discovery. By studying the remnants of these events, we might finally decode the properties of actions, their mass, their coupling strength, even their role in shaping the universe. Telescopes like Fermi LT and future gravitational wave observatories could be the key, scanning the skies for the telltale fingerprints of these cataclysms. So while the idea of a black hole bomb might sound like science fiction, it's rooted in the cold, hard equations of quantum field theory, and that makes it one of the most thrilling possibilities in modern physics. Cosmic inflation, the idea that the universe underwent a staggering expansion in its first fraction of a second, is one of the most elegant solutions to cosmology's biggest puzzles. But what if actions weren't just bystanders to this explosive growth? What if they were the engine behind it? That's the radical premise of action inflation, a theory where these ghostly particles don't just explain dark matter. They might have shaped the very fabric of spacetime itself. At the heart of this idea lies the action's unique potential energy landscape. Unlike ordinary particles whose behavior is dictated by simple, bowl-shaped potentials, actions oscillate in a periodic field. Think of a washboard pattern with countless dips and rises. In the early universe's extreme conditions, this structure could have triggered a phenomenon called slow roll inflation, where the action field gets temporarily trapped on one of those high-energy ridges. As it gradually rolls downward, it releases energy so efficiently that it drives exponential expansion, stretching quantum fluctuations into the seeds of galaxies. But here's where things get truly fascinating. As inflation ends and the action field settles into its lowest energy state, it wouldn't just vanish. Instead, the energy stored in those oscillations would fragment into action particles themselves, like a cosmic pendulum finally coming to rest, its motion dissipating into trillions of tiny waves. These remnants, born from the death throes of inflation, could be the very dark matter we're searching for today. It's a breathtaking two-for-one deal. Actions both stretch the universe and then fill it with invisible mass. Critically, this scenario solves one of inflation's lingering mysteries, the initial condition problem. Why did inflation start in the first place? Actions offer an elegant answer. Their periodic potential naturally allows for multiple starting points, making the trigger statistically inevitable across a vast multiverse. Some models even suggest that the action's decay could imprint subtle signatures on the cosmic microwave background, specific patterns in polarization or non-Gaussian fluctuations that upcoming telescopes might spot. The implications stretch beyond theory. If action inflation is real, it would mean dark matter isn't just an accident of particle physics, it's a fossil from the universe's most transformative moment. And that changes everything. Suddenly, the same particle explaining why galaxies hold together could also tell us why the cosmos looks so uniform, so flat on the largest scales. It's a thread tying together two of cosmology's deepest puzzles, with actions as the silent architects of our reality. Of course, not all scientists are convinced. Critics point out that action inflation requires finely tuned parameters to match observations, and alternative models like chaotic inflation remain strong contenders. But that's the beauty of this field. Every challenge sparks new ideas. Some theorists now explore hybrid scenarios where actions team up with other fields to drive inflation, or even propose that multiple action fields interacted in a cosmic symphony. For now, the hunt for evidence is on. Experiments searching for primordial gravitational waves, ripples from inflation itself, could find hints of action-driven expansion. Others are reanalyzing CMB data for those telltale fingerprints, and if we're lucky, the answer might come from an entirely unexpected direction, like a lab detection of actions revealing properties that only make sense if they once powered the universe's birth. One thing's certain, if action inflation is correct, it would rewrite not just the story of dark matter, but the very origin of everything. The same particles drifting unseen through your room right now might have once unleashed the most violent creative force in existence. And that's a connection worth marveling at. Among the countless theories about actions, one stands out not just for its elegance but for how tightly it pins down the particle's properties, the QCD action window. This isn't some vague, open-ended range. It's a razor-thin band of possible masses between 1 and 100 microelectron volts, where actions don't just exist but solve two of physics' greatest puzzles at once. Think of it like a cosmic master key, one small enough to slip through the eye of a needle, yet capable of unlocking both the mystery of dark matter and the stubborn strong CP problem. Why this exact range? It all comes down to quantum chromodynamics, or QCD, the theory governing how quarks and gluons interact. The strong CP problem hinges on a question: why does this force seem to ignore certain symmetry violations that, mathematically, should warp the behavior of particles? The action's original purpose was to restore that symmetry, acting as a kind of cosmic reset button. But for it to work, the action's mass couldn't be arbitrary. Too heavy, and it would have been spotted in particle colliders decades ago. Too light, and its interactions would be so feeble it couldn't have shaped the universe as we see it. The sweet spot where the action's mass and coupling strength align perfectly lands squarely in that 1 to 100 microelectron volt window. But here's where it gets even more precise. If actions in this range make up dark matter, their abundance would naturally match what we observe in the cosmos. The math reveals something almost poetic. The action's mass determines how densely it clumps in the early universe. Lighter actions would behave like a diffuse fog, failing to account for the gravitational pull we measure in galaxies. Heavier ones would clump too aggressively, creating dense structures that don't match the smooth halos we detect. But within this narrow band, the numbers align so perfectly it's hard to dismiss as coincidence. This precision is why experiments like ADMX and Haystack are laser-focused on the QCD window. Their detectors are essentially ultra-sensitive radios, tuned to the exact frequencies where actions in this mass range would sing when exposed to strong magnetic fields. Imagine trying to catch a whisper in a hurricane, except you know the whisper's exact pitch. That's the level of fine-tuning these experiments achieve. Yet the window isn't just a target, it's also a deadline. If actions exist within this range and solve both problems, we're on the verge of finding them. If not, the entire paradigm might need rethinking. That's the thrill and the tension of this search. Every tweak to a detector's sensitivity, every new run of data, brings us closer to answering whether this elegant idea is a stroke of genius or a beautiful dead end. And that's what makes the QCD action window more than a theory. It's a test of whether the universe plays by the rules we've dared to imagine. Galaxies shouldn't hold together the way they do. According to gravity alone, the outer stars in spiral galaxies should fling away like riders tossed from a carousel, yet they don't. Dark matter's invisible grip explains this, but there's a catch. Some dwarf galaxies rotate too smoothly for the standard predictions. Their dark matter halos appear less clumpy than simulations suggest. Enter actions with their uncanny ability to form solitonic cores, dense, wave-like balls of dark matter at the heart of galactic halos. These aren't just theoretical curiosities, they could be the missing piece in our galactic puzzles. Picture a solitonic core as something between a fog and a whirlpool, an immense, coherent quantum wave hovering at a galaxy's center. Because actions are ultralight, their quantum nature dominates on cosmic scales. Instead of behaving like discrete particles, they overlap like ripples in a pond, creating a standing wave that resists dispersion. Gravitational pull concentrates these waves into dense knots, while quantum pressure prevents them from collapsing further. The result, a smooth, gradient-like halo that transitions seamlessly into a dense core, perfectly matching the rotation curves of problematic dwarfs like Dragonfly 44 or the ultra-diffuse galaxies that baffled astronomers. What makes solitonic cores so compelling is how naturally they emerge from action physics. Simulations of fuzzy dark matter, a close cousin to axions, show these cores forming in every galaxy, with sizes inversely tied to the axion's mass. Lighter axions produce larger cores, while heavier ones create compact knots. When researchers plugged in axion masses around 10 to the minus 22 electron volts, the simulated halos mirrored real-world observations down to the slightest detail. Stars orbiting these cores move exactly as observed, without the need for finely tuned clumpiness. It's as if the universe handed us a recipe: take 1 part quantum weirdness, mix with gravity, and bake for 13 billion years. But the implications stretch beyond dwarf galaxies. Solitonic cores could explain why we don't see as many small satellite galaxies as simulations predict. Traditional dark matter models produce halos that fragment too easily, spawning swarms of tiny satellites. Axion cores, by contrast, suppress fragmentation. Their wave-like nature smooths out minor density fluctuations, leaving fewer seeds for satellite formation. This might finally resolve the missing satellites problem that's plagued astrophysics for decades. The smoking gun could lie in stellar motions near galactic centers. If solitonic cores exist, stars closest to them should orbit with a distinct velocity pattern, slow near the core's edge, then rising sharply toward the center. Telescopes like the upcoming Vera Rubin Observatory are poised to test this, mapping stellar speeds with unprecedented precision. Already, studies of the Milky Way's own core hint at anomalies that align eerily well with axion predictions. Yet the most tantalizing clue might come from collisions. When galaxies merge, their dark matter halos should lag behind the visible stars, but solitonic cores resistant to disruption would cling tighter to their galaxies. Recent observations of the Bullet Cluster, a cosmic collision where dark matter and stars separated cleanly, show hints of this very behavior. It's as if dark matter remembered where it belonged, exactly what a coherent quantum wave would do. So while axion halos might sound like an abstract fix, they're grounded in observable reality. They don't just tweak the rules, they rewrite them in a language the universe seems to understand. And if we're right, these ghostly cores aren't just hiding in dwarf galaxies, they're everywhere, weaving the quantum and the cosmic into a single, elegant tapestry. What if the night sky hides explosions we can't see, bursts of energy with all the fury of a supernova, but no star at their core? That's the spine-tingling possibility of axion-boson nova, a phenomenon where vast clouds of dark matter could detonate in silent, ghostly fireworks. Picture this: a colossal axion-boson Einstein condensate, light years across, drifting through the emptiness of space. Over eons, gravity slowly pulls it tighter, denser, until quantum forces can no longer hold it back. In an instant, the entire structure collapses, releasing energy not through nuclear fusion, but through the violent conversion of axions into photons. The result, a blinding flash of gamma rays erupting from nowhere, visible across the cosmos, yet leaving no neutron star or black hole behind. This isn't just a thought experiment. The math reveals something startling. Unlike normal stars, which explode when their cores buckle under gravity, axion condensates would implode due to a quantum mechanical instability. As the axion waves compress, their energy density skyrockets until they reach a critical threshold, triggering a runaway process where axions rapidly convert into photons. Simulations suggest these events could outshine entire galaxies for brief, brilliant moments, with spectra unlike any known astrophysical source. Some researchers speculate that rare, unexplained gamma-ray bursts like GRB 070614, which lacked a visible host galaxy, might be the smoking guns of these dark matter detonations. What makes axion-photon nova so tantalizing is their potential to solve multiple mysteries at once. Their unique emission patterns could account for anomalies in the cosmic gamma-ray background, the diffuse glow that permeates space. They might also explain so-called orphan afterglows, flashes of light with no detectable progenitor, that have puzzled astronomers for years, and because axion explosions would occur far from conventional stellar environments, they'd leave no chemical traces in interstellar gas, making them truly invisible except in their final, radiant moments. The hunt for evidence is already underway. Telescopes like Fermi are scanning the skies for gamma-ray signatures that match the predicted spike and fade profile of an axion collapse. Others are digging through archival data, searching for bursts that defy classification. If we're lucky, one of these could be the Rosetta Stone, a cosmic message written in the language of dark matter's death throes. But here's the most mind-bending part. If axion-photon nova are real, they'd prove that dark matter isn't just passive scaffolding. It's dynamic, capable of its own brand of cataclysmic violence. The universe might be teeming with these invisible explosions, their light piercing the dark in fleeting, brilliant testament to the unseen forces shaping our cosmos. And we're only just learning how to look. The universe's two greatest mysteries, dark matter and dark energy, might not be separate enigmas at all. Imagine if the same invisible hand guiding galaxies' rotation also drives the cosmos' accelerating expansion. That's the bold promise of axion quintessence unification, where a single, evolving scalar field could wear two hats, as the axion, clumping into dark matter's ghostly halos, and as quintessence, the elusive force stretching space itself. At first glance, they seem worlds apart. Dark matter pulls, sculpting galaxies with gravity's grip, while dark energy pushes, flinging galaxies apart on an unseen tide. Yet beneath the surface, both could spring from the same quantum source, a field whose potential shifts over cosmic time, changing its role like an actor playing dual parts in the universe's grand play. Picture this field as a cosmic chameleon. In the early universe, when matter was dense and temperatures high, it oscillated rapidly, its energy behaving like a collection of discrete particles' actions. These would condense into the dark matter scaffolding we observe today. But as the universe expanded and thinned out, the field's potential energy plateaued, its oscillations slowing to a near standstill. Now, instead of masquerading as particles, it manifests as a smooth, persistent force, quintessence, the driver of cosmic acceleration. The math behind this transformation is startlingly elegant. The same field that once solved the strong CP problem could also explain why the universe's expansion isn't just continuing, it's speeding up. Critically, this isn't just theoretical sleight of hand. The axion quintessence idea makes testable predictions. If the field's potential has the right shape, steep enough to produce axions early on, then shallow enough to mimic dark energy later, its imprint should linger in the large-scale structure of the cosmos. The distribution of galaxy clusters, for instance, might show subtle correlations between dark matter clumping and the onset of accelerated expansion. Even more tantalizing, the field's slow roll phase could leave fingerprints in the cosmic microwave background's polarization patterns, hints of a unified origin hiding in plain sight. But the real breakthrough would come from axion detection itself. If experiments like ADMX find axions with specific masses and coupling strengths, it could narrow down the exact form of the quintessence potential, turning a vague idea into a precise cosmic blueprint. Conversely, if dark energy's behavior shifts over time, something future telescopes like Euclid aim to measure, it might point back to the axion's dual nature. The pieces of this puzzle are scattered across disciplines, from particle physics to cosmology, waiting to be connected. What's mesmerizing is how this theory flips the script. Instead of two unrelated unknowns plaguing our models, we'd have a single framework where dark matter and dark energy are phases of the same underlying reality, like ice and steam, different faces of water. It's a vision as audacious as it is beautiful, suggesting the universe's greatest puzzles might share a solution hiding in the quantum shadows. And if we're right, uncovering that connection wouldn't just fill gaps in our understanding, it would rewrite the story of everything. Some of the most intriguing hints of actions don't come from dark matter searches at all, but from experiments designed to catch an entirely different ghostly particle, the neutrino. In 2020, the Xenon 1T detector, buried deep beneath Italy's Gran Sasso mountain, picked up an unexpected bump in its data, a faint excess of electron recoil events that defied easy explanation. While some chalked it up to tritium contamination, others noticed something peculiar. The signal's energy matched predictions for solar actions interacting with the detector's liquid xenon. But here's the twist: it wasn't just actions alone that could explain the anomaly. Theorists soon realized the data might point to something even stranger: actions and neutrinos talking to each other through a hidden quantum channel. This idea isn't as far-fetched as it sounds. Neutrinos are already shape-shifters, oscillating between flavors as they travel. What if actions could influence that process? Certain beyond the standard model theories propose that actions and neutrinos share a coupling, a kind of quantum handshake mediated by yet another hypothetical particle called a majoron. In this scenario, solar actions wouldn't just convert directly into detectable signals. Instead, they'd first morph into neutrinos, which then interact with electrons in the detector, creating the observed recoil pattern. It's a cosmic game of telephone, with the action's whisper passing through the neutrino before reaching our instruments. The implications ripple far beyond one experiment. If actions and neutrinos mix, it could solve multiple puzzles at once. Take the so-called neutrino luminosity problem. The fact that the Sun seems to emit fewer neutrinos than our models predict. Action neutrino oscillations might offer an escape clause, with some solar neutrinos converting into actions mid-flight, effectively vanishing from our detectors. Even more provocative are hints from IceCube, the Antarctic Neutrino Observatory, where high-energy neutrinos appear to arrive from certain directions more often than chance allows. Could action neutrino interactions bend their paths, steering them like invisible lenses? Experiments are already adapting to test these ideas. Next-generation detectors like Darwin and Panda XXT will scrutinize the Xenon 1T excess with improved sensitivity, while projects like JSNS-2 in Japan hunt for sterile neutrinos that might serve as middlemen in action neutrino mixing. The beauty of this search lies in its sheer breadth. Action neutrino couplings could manifest in everything from supernova neutrino bursts to distortions in the cosmic neutrino background. What's exhilarating is how this blurs the line between dark matter and neutrino physics. We might be witnessing the birth of a new paradigm, where the universe's most elusive particles aren't just neighbors but collaborators in a hidden quantum dance. And each anomaly, each glimmer in the data, brings us closer to hearing the music. What if dark matter isn't made of solitary, ghostly particles drifting through space, but cosmic nuggets, dense chunks of actions and quarks lurking in the void? That's the radical premise of the action-quark nugget model, or ACON, a theory so bold it tackles two of physics' biggest puzzles in one stroke. Imagine a scenario where the early universe didn't just produce actions as free-floating waves, but forged them into macroscale objects, some as small as a grain of sand, others rivaling asteroids, each one a bizarre hybrid of dark and ordinary matter. These nuggets wouldn't just explain dark matter's gravitational pull. They could also solve the mystery of baryogenesis, the puzzling imbalance between matter and antimatter that makes our existence possible. The Equine model begins with a dramatic twist on action formation. In most theories, actions condense into diffuse clouds or waves, but here they interact so strongly with quarks in the primordial plasma that they trigger a kind of cosmic phase transition. Picture a pot of boiling water suddenly freezing, except instead of ice, you get ultra-dense blobs of quark matter wrapped in action fields. These nuggets form thanks to a phenomenon called charge segregation, where the action fields oscillations separate quarks and antiquarks, preventing them from annihilating entirely. The result: stable, long-lived objects carrying a remnant of the universe's original matter-antimatter asymmetry, frozen in time like cosmic fossils. What's astonishing is how these nuggets could evade detection while shaping the cosmos. Their quark cores would be neutral, emitting no light, while their action shells suppress interactions with ordinary matter. Yet their sheer mass, some weighing tons, means they'd bend spacetime subtly, acting like invisible mini-black holes. This could explain why some microlensing surveys spot gravitational anomalies without any visible cause. Even wilder, equines might leave traces in unexpected places. When one collides with a neutron star, the impact could release a burst of radio waves, while nuggets plowing through Earth's atmosphere might produce unusual ionospheric disturbances or even high-altitude explosions mistaken for meteors. The most provocative claim, though, is how equines could solve baryogenesis. Standard cosmology struggles to explain why matter outweighs antimatter by a billionth of a percent. Just enough to allow stars, planets, and us to exist. The equine model flips the script. Instead of matter barely winning, it suggests antimatter did dominate initially, but became locked inside action quark nuggets, invisible and inert. Ordinary matter, left unchallenged, then shaped the universe we see. It's a cosmic sleight of hand where dark matter isn't just a spectator, but the hidden architect of reality's asymmetry. Of course, the theory has skeptics. Critics argue that equines should have left clearer imprints in cosmic microwave background data or produced observable annihilation signals. Yet proponents counter that nuggets could be rarer or cooler than assumed, their signatures buried in noise. Experiments like SKA and future gravitational wave detectors might settle the debate, hunting for nugget-induced radio bursts or spacetime ripples. Whether equines exist or not, their audacity captures the spirit of action research, a field where even the wildest ideas might hold kernels of truth. After all, in a universe filled with invisible mass and unexplained asymmetry, why couldn't dark matter take the form of ancient quark-stuffed relics? The answer, as always, lies in the data and the patience to keep searching. One of the most ingenious ways to hunt for action quark nuggets doesn't involve particle detectors or underground labs. It relies on the faint glow of heat. If these exotic objects exist, they might be silently radiating away their energy in the infrared spectrum, leaving a thermal fingerprint across the cosmos. Here's why: even though equines are cloaked in action fields, their quark cores aren't perfectly insulated. Over billions of years, interactions within the nugget, like quark collisions or magnetic field decay, could generate tiny amounts of heat, causing them to emit thermal radiation at temperatures just a few degrees above absolute zero. That's far too cold for visible light, but it's right in the sweet spot for infrared telescopes scanning the heavens. This isn't just speculation. Models suggest that equines, depending on their size and age, would glow faintly at wavelengths between 10 and 100 micrometers, a range where the universe's background noise is relatively low. The trick is distinguishing their signal from the countless other sources of infrared radiation, like interstellar dust or distant galaxies. That's where all sky surveys come in. Projects like NASA's WISE telescope and the upcoming SPHEREX mission are mapping the infrared sky with unprecedented sensitivity, cataloging millions of point sources. Hidden in that data could be the telltale signatures of equines, objects that don't match known stellar or galactic profiles, drifting slowly against the backdrop of the cosmos. What makes these searches so compelling is their ability to probe a wide range of AQN masses. Smaller nuggets warmed by internal processes might appear as faint, isolated infrared dots. Larger ones could be cooler but more massive, subtly distorting the light of background stars through gravitational microlensing. Some theorists even propose that AQNs could explain certain anomalous microwave emissions, mysterious signals detected by telescopes like Planck, which defy conventional astrophysical explanations. If these emissions stem from thermal photons redshifted over cosmic distances, they might trace back to a population of ancient cooling nuggets. The hunt isn't without challenges. AQN thermal signals would be achingly faint, often buried in the noise of cosmic infrared backgrounds, but clever statistical techniques could tease them out. By stacking data from multiple surveys or cross-referencing infrared catalogs with gravitational lensing maps, researchers might spot patterns invisible to the naked eye. Even more tantalizing, some models predict that AQNs could occasionally flare when passing through dense regions like molecular clouds, their quark surfaces sparking bursts of detectable radiation. If infrared surveys do uncover these thermal ghosts, it would revolutionize our understanding of dark matter, not as a swarm of particles, but as a cosmic legacy of the universe's earliest and most violent phase transitions. And that's what makes this search so thrilling. We're not just looking for invisible mass, we're hunting for the echoes of a time when matter itself was forged in conditions we can scarcely imagine. Fast radio bursts, those fleeting, ultra-powerful blips of cosmic radiation, have puzzled astronomers since their discovery in 2007. Lasting just milliseconds, these bursts pack more energy than the sun emits in weeks, yet their origins remain shrouded in mystery. But what if the answer lies not in collapsing stars or alien signals, but in the ghostly dance of actions around some of the universe's most extreme objects? Enter magnetars, neutron stars with magnetic fields so intense they distort the very fabric of space. These cosmic powerhouses could be the perfect stage for axion-photon conversions on a staggering scale, turning whispers of dark matter into the universe's loudest radio screams. Picture a magnetar's magnetosphere, a seething labyrinth of twisted magnetic field lines, crackling with pent-up energy. Now imagine actions drawn by the star's immense gravity, spiraling into this turbulent zone. As they skim the edges of those magnetic fields, something extraordinary happens. The actions shake off their invisibility, converting explosively into radio photons through a process akin to a quantum lightning strike. The result, a shockwave of electromagnetic energy racing outward at light speed, detectable across billions of light-years as an FRB. What makes this idea so compelling is the math. The burst durations, frequencies, and even their polarized signatures align eerily well with predictions for axion-photon interactions in such extreme environments. There's even a smoking gun in the data. Some repeating FRBs exhibit bizarre downward frequency drifts like a cosmic slide whistle that conventional astrophysical models struggle to explain. Axion conversions naturally produce this effect. As the burst propagates through the magnetosphere, higher frequency photons escape first, while lower frequencies lag slightly, creating that telltale drift. It's a fingerprint that could distinguish axion-driven bursts from other sources. But the wildest implication isn't just explaining FRBs, it's turning them into dark matter probes. If axions power these bursts, their properties would be encoded in the radio signal's fine structure. The burst brightness could reveal the axion-photon coupling strength, while the spacing between repetitions might hint at the axion's mass. Telescopes like CHIME and FAST are now scanning for these subtle clues, treating each FRB as a potential message from the dark sector. Of course, skeptics point out hurdles. Magnetars are rare, and not all FRBs trace back to them. Yet alternative models suggest axion conversions could also ignite bursts in primordial black hole magnetospheres or even within axion stars undergoing collapse. The common thread: these theories transform FRBs from cosmic oddities into potential floodlights, illuminating the invisible action we suspect surrounds us all. Whether the link holds or not, one thing's certain: the universe keeps finding ways to surprise us, and actions might be its most unexpected messengers yet. One of the most persistent criticisms haunting action theories isn't about detecting the particles, it's about why they exist with such bizarrely precise properties in the first place. Welcome to the action quality problem, a puzzle that cuts to the heart of whether these particles are elegant solutions or cosmic coincidences. At first glance, actions seem perfectly tailored to solve both the strong CP problem and dark matter. But that perfection comes at a cost. The math reveals something unsettling. For actions to work as intended, their potential energy landscape must be exquisitely flat, so flat that even the tiniest quantum corrections or gravitational effects should warp it beyond recognition. It's like balancing a pencil on its tip for billions of years while the universe constantly tries to knock it over. This fine-tuning dilemma has led some physicists to question whether actions are truly natural or just a theoretical sleight of hand. The core issue lies in something called the action decay constant, a parameter that dictates how strongly actions interact and how much they weigh. For actions to solve both the strong CP problem and account for dark matter, this constant must fall within an absurdly narrow range. Too high, and actions would be too weakly coupled to matter, rendering them irrelevant. Too low, and they'd have been spotted in particle colliders decades ago. The window that works is so precise it feels suspicious, as if the universe dialed in these numbers by hand. But here's where things get interesting. Theoretical physicists have proposed two bold escape routes from this fine-tuning trap. The first leans on extra dimensions specifically, the idea that actions aren't just four-dimensional fields but higher-dimensional ones, their properties protected by symmetries hidden in the geometry of compactified space. Picture an action's potential not as a simple washboard but as a complex, multidimensional surface where certain directions are shielded from destabilizing effects. String theory offers particularly compelling versions of this, where action stability emerges naturally from the way extra dimensions curl and vibrate. The second solution is far more controversial: anthropic selection. If our universe is just one bubble in a vast multiverse, each with randomly varied action parameters, then it's no surprise we find ourselves in a bubble where the numbers lined up just right for life to exist. In this view, fine-tuning isn't a flaw, it's a selection effect. We couldn't observe a universe where actions failed to balance because galaxies and physicists wouldn't have formed there in the first place. While this idea makes some scientists recoil, critics dismiss it as giving up on fundamental explanations. Others argue it's the only way to reconcile the eerie precision we observe. Strikingly, these approaches aren't mutually exclusive. Some hybrid models combine extra-dimensional protection with multiverse reasoning, suggesting that while higher dimensions stabilize actions broadly, anthropic selection picks out the specific versions compatible with complex structures like stars and planets. The debate remains wide open, with experimentalists racing to test predictions from each camp. If future action searches find the particles' mass and couplings falling precisely into that too good to be true sweet spot, it might nudge us toward the multiverse explanation. Conversely, discovering unexpected deviations could point to hidden symmetries in extra dimensions. What's fascinating is how this quality problem mirrors broader tensions in physics between naturalness and fine-tuning, between top-down and bottom-up explanations. Actions have become a microcosm of the discipline's deepest philosophical divides, and that's what makes them more than just hypothetical particles. They're a litmus test for how we think the universe ought to work, whether it's a clockwork of perfect symmetries, a dice roll of infinite possibilities, or something stranger still. The answer, if we find it, won't just tell us about dark matter. It'll tell us whether our cosmic home is inevitable, improbable, or something beyond our current imagination. Primordial black holes, those mysterious remnants from the universe's first moments, have long been proposed as dark matter candidates. But what if they're not acting alone? Imagine a scenario where these ancient gravitational behemoths team up with axions, creating a hybrid dark matter system that leaves fingerprints no single component could. Here's how it works. Primordial black holes, born from density fluctuations in the early cosmos, would naturally gather clouds of axions around them like cosmic lint. Axions, being ultra-light and quantum by nature, wouldn't just orbit these black holes, they'd form vast, coherent waves trapped in gravitational embrace. The result, a black hole dressed in a shimmering quantum cloak, its presence magnified by the axion halo's eerie properties. This partnership solves multiple puzzles at once. On their own, primordial black holes face strict constraints. Too many would disrupt star clusters or warp the cosmic microwave background in ways we don't observe. But pair them with axion clouds and the math shifts dramatically. The axions wave like nature spreads their mass smoothly, softening the black hole's gravitational footprints. Simultaneously, the black hole's gravity amplifies axion detection prospects. When axion waves oscillate near a black hole's event horizon, they don't just hum quietly, they resonate, converting gravitational energy into detectable signals. Some models suggest these interactions could produce faint but distinctive gravitational wave chirps, a cosmic duet between space-time ripples and quantum oscillations. The most tantalizing possibility, axion clouds might explain why we haven't spotted primordial black holes yet. If they're wrapped in dense axion halos, their lensing effects could differ subtly from naked black holes, camouflaging them in plain sight. Telescopes hunting for microlensing events might be overlooking these hybrid objects because their signatures don't match expectations. Even wilder, collisions between axion-dressed black holes could release bursts of low-frequency gravitational waves, a signature future observatories like LISA are perfectly tuned to catch. But the real magic lies in the early universe. During cosmic dawn, axion clouds around primordial black holes could have acted as gravitational seeds, accelerating the formation of the first galaxies. Their combined gravity would pull in gas and dark matter far more efficiently than either could alone, potentially explaining why some galaxies formed shockingly fast. It's a cosmic loophole, two dark matter candidates, each incomplete on their own, joining forces to shape the universe in ways we're only beginning to decipher. The hunt for these paired phenomena is already reshaping astrophysics. From reanalyzing quasar lensing anomalies to designing algorithms that pick axion black hole harmonics out of gravitational wave data, researchers are chasing shadows that might rewrite the dark matter playbook. And if they succeed, we won't just have solved a mystery, we'll have uncovered a hidden collaboration operating since the dawn of time. Galaxy clusters are cosmic powerhouses, swirling with ultra-hot gas and tangled magnetic fields that stretch across millions of light-years. Within this chaos, something extraordinary might be happening. Axions, those ghostly dark matter candidates, could be revealing themselves through a celestial magic trick. Picture a lone axion drifting through the heart of a galaxy cluster, where magnetic fields are so intense they twist like invisible cyclones. As it traverses this turbulent zone, the particle's quantum nature allows it to momentarily shed its invisibility, transforming into an X-ray photon. It's as if the galaxy itself is whispering its secrets in a language of high-energy light. This phenomenon, axion-photon oscillation, isn't just theoretical sleight of hand. NASA Chandra X-ray Observatory has spotted puzzling excesses of X-ray emissions from galaxy clusters like Perseus and Coma, where the signal defies conventional astrophysical explanations. The energy of these X-rays, around 3.5 kiloelectronvolts, lines up eerily well with predictions for certain axion masses. Even more compelling, the emissions appear concentrated around the cluster's central regions, where magnetic fields are strongest, exactly where axion conversion should peak. Skeptics argue it could be an exotic atomic process, but no known element matches this spectral signature so precisely. The implications stretch far beyond a single observation. If axions are behind these X-rays, their conversion rate would encode details about both their mass and how strongly they couple to photons, a direct window into dark matter's quantum properties. Galaxy clusters, with their extreme environments, become natural laboratories, amplifying signals too faint to detect elsewhere. Future X-ray missions like Athena or Lynx could map these emissions in unprecedented detail, turning entire galaxies into axion detectors. Yet the most tantalizing clue lies in the polarization of these X-rays. Axion conversions would twist the light's electric field orientation in a unique way, leaving a fingerprint distinct from any astrophysical process. Current telescopes lack the resolution to confirm this, but next-generation instruments might crack the code. If they do, we won't just have indirect hints, we'll have a smoking gun, proving that dark matter has been hiding in plain sight, illuminating the cosmos in X-rays we're only now learning to decipher. Imagine standing outside on a windy day, feeling the breeze push against you as Earth hurtles through space. Now replace that breeze with something far stranger, a silent, invisible wind of axions, streaming past us as our planet moves through the galaxy's dark matter halo. This isn't just poetic imagery, it's a real phenomenon with groundbreaking implications for how we hunt these elusive particles. Every second, as Earth orbits the Sun and the Sun swings around the Milky Way's core, we're plowing through the galactic axion halo at roughly 230 kilometers per second. That movement creates a distinct wind of axions blowing from the direction of the constellation Cygnus, and if we're clever enough, we might be able to catch it. Directional detection is the key. Most axion searchers like ADMCs treat these particles as if they're evenly distributed, like a fog hanging motionless in space. But if axions make up dark matter, they shouldn't be stationary. They should flow with the galaxy's rotation, creating a detectable headwind as Earth moves against the current. Think of it like driving through rain. The droplets don't just fall vertically, they streak diagonally across your windshield because of your car's motion. Similarly, axion signals should carry a subtle frequency shift, a Doppler effect based on Earth's direction and speed through the halo. This idea has sparked bold new experimental designs. One proposal involves using quantum sensors arranged in a spherical array, each tuned to pick up faint axion-induced electromagnetic waves. By comparing signals across the array, researchers could triangulate the wind's direction, turning the entire detector into a cosmic weather vane for dark matter. Another approach leverages nuclear magnetic resonance. Imagine atoms acting like tiny compass needles, wobbling slightly when buffeted by the axion wind. Advanced versions of these experiments, like Casper or Quax, are already probing these directional hints, searching for patterns that align with Earth's predicted motion. But here's where it gets even more intriguing. The axion wind shouldn't be perfectly uniform. Just as Earth's orbit isn't a perfect circle, variations in the solar system's speed and the galaxy's gravitational field could imprint subtle gusts and lulls in the flow. Some models even suggest that local dark matter clumps, miniclusters born from the axion field's early quantum fluctuations, might create intermittent spikes in the wind's intensity. If we could map these fluctuations, we'd gain unprecedented insight into the Milky Way's hidden structure, tracing the gravitational scaffolding of our galaxy through its ghostly currents. Timing adds another layer. Because Earth's velocity changes as it orbits the Sun, the axion wind should wax and wane over the course of a year. Experiments running continuously could hunt for this annual modulation, a telltale sign that they're not just seeing noise but actual dark matter. Intriguingly, a similar yearly signal has already been spotted in some direct detection searches for heavier dark matter particles, though results remain controversial. If axion experiments find matching patterns, it could be the smoking gun we've waited decades for. What makes directional detection so revolutionary isn't just the chance to prove actions exist, it's the opportunity to study dark matter's galactic geography firsthand. By measuring the wind's speed and direction, we could reconstruct the Milky Way's dark matter halo in 3D, revealing whether it's shaped like a smooth sphere, a flattened disk, or something more exotic. It's like being handed a map to the invisible half of our universe, one gust of actions at a time. And with every advance in quantum sensing and ultra-low noise amplifiers, we edge closer to feeling that cosmic breeze for real, transforming a theoretical wind into the first tangible touch of the dark cosmos. For decades, the leading explanation for dark matter was the WIMP, a weakly interacting massive particle. These hypothetical heavyweights, thought to be 100 times the mass of a proton, promised an elegant solution to the universe's missing mass. Their interactions would be just feeble enough to avoid detection, yet strong enough to leave traces in particle colliders. This perfect balance became known as the WIMP miracle, a cosmic coincidence so precise it seemed almost destined. But as experiments like Xenon and LUX kept coming up empty, the WIMP paradigm began to crack under the weight of its own expectations. Enter Axions, a radically different vision of dark matter that sidesteps the WIMP crisis entirely while still explaining the same cosmic evidence. Axions flip the script on nearly every WIMP assumption. Where WIMP are heavy, Axions are almost unimaginably light, billions or trillions of times less massive than electrons. Where WIMP interact through the weak nuclear force, Axions couple primarily to electromagnetism and gravity. And where WIMP were expected to leave dramatic signals in underground detectors, Axions whisper their presence through subtle quantum conversions. Yet despite these contrasts, both particles share one crucial trait. They fit the observed distribution of dark matter in galaxies and clusters with uncanny precision. The difference lies in how they achieve it. WIMP rely on a process called thermal freeze-out, where early universe collisions eventually left behind a relic density matching today's dark matter. Axions, however, emerge from coherent quantum oscillations, a non-thermal process where their field's energy directly condenses into particles. This distinction solves multiple headaches at once. The WIMP miracle's downfall came from its need for specific cross-sections interaction strengths that had to be just right to produce the correct abundance. Axions bypass that entirely. Their density is set by the initial conditions of the universe, not by particle physics fine-tuning. Even more compelling, Axions naturally avoid the small-scale crises plaguing WIMP, like the missing satellite problem or the too smooth cores of dwarf galaxies. Ultralight Axions' wave-like behavior suppresses small-scale clumping, smoothing out halos in ways that match observations without needing messy feedback mechanisms. But perhaps the most striking contrast is in detection. WIMP were supposed to reveal themselves through nuclear recoils, rare collisions with atomic nuclei in vats of liquid xenon or argon. After decades of ever larger detectors finding nothing, the parameter space for viable WIMP has shrunk to a sliver. Axions, though, offer entirely different avenues, from microwave cavities hunting for photon conversions to telescopes probing subtle stellar anomalies. Where WIMP demanded brute force sensitivity, Axion searches rely on quantum ingenuity. That's not to say Axions are flawless. The QCD Axions' tight mass range walks its own fine-tuning tightrope, and some models still struggle to explain certain large-scale structures. But what makes the Axion paradigm so compelling is its resilience. While WIMP hinged on a single detection method now facing a crisis, Axions offer a web of complementary approaches, each failure narrowing the search rather than invalidating the theory. It's a reminder that dark matter might not be a monolithic puzzle but a layered mystery, with answers hiding where we least expected. And if Axions are the key, they're rewriting the rules of the game, entirely turning the WIMP miracle's collapse into a stepping stone toward something far stranger. What if the universe didn't just stumble upon the perfect conditions for life, but was selected for them? That's the spine-tingling premise of the anthropic axion, a theory that takes fine-tuning from a puzzle to a cosmic inevitability. Imagine a vast multiverse bubbling with countless universes, each governed by different physical laws. In most, the axion's properties might be too weak to form dark matter or too strong to allow galaxy formation. But in a rare subset like ours, the numbers align just right, not by chance, but because only those universes can spawn observers to ponder the mystery. This idea turns the axion quality problem on its head. Instead of asking why axions seem improbably fine-tuned, anthropic reasoning suggests they had to be. If axions were much heavier, their rapid early universe oscillations would have diluted matter too unevenly, preventing stable galaxies, too light, and they'd fail to clump into the halos that sculpt cosmic structure. The narrow window where axions solve both dark matter and the strong CP problem isn't a fluke. It's the only window where life could arise to notice it. Critics dismiss this as a cop-out, a way to sidestep deeper explanations, but proponents point to eerie coincidences. The axion decay constant, that crucial parameter determining its mass, aligns suspiciously well with the scale needed for habitable galaxies. Even the axion's coupling to photons seems just enough to avoid disrupting stellar chemistry while still leaving detectable hints. It's as if the universe threaded a needle and we're the thread. The multiverse angle adds a provocative twist. If other universes exist with random axion parameters, most would be barren wastelands. We find ourselves in a Goldilocks universe not because it's special, but because it's necessary. This isn't metaphysics, it's testable. If future experiments find axions perched precisely in that habitable slice of parameter space, it would bolster the anthropic view. Conversely, deviations could point to hidden symmetries instead. Yet the anthropic axion isn't just about dark matter. It reshapes how we see all fine-tuning in physics, from the cosmological constant to particle masses. Maybe the universe isn't fine-tuned for us, we're simply the inevitable byproduct of the few universes where tuning allowed complexity to emerge. And that's the real mind-bender. The axion's ghostly properties might not just explain the cosmos we see. They could reveal why we're here to see it at all. Quantum gravity has long been the holy grail of theoretical physics, a framework to unite Einstein's general relativity with the bizarre rules of quantum mechanics. Most attempts, from string theory to loop quantum gravity, stumble over how to reconcile smooth spacetime with the granularity of quantum fields. But there's a surprising twist. Axions, those lightweight dark matter candidates, might hold the key to bridging this divide. In certain quantum gravity models, axions emerge naturally as Goldstone bosons particles born from the spontaneous breaking of spacetime symmetries. Picture the fabric of the universe as a vast, elastic sheet. When this sheet stretches or twists in specific ways, it can create ripples, not just gravitational waves, but quantum oscillations that manifest as axions. These symmetries aren't arbitrary. They're tied to the underlying geometry of spacetime itself. For instance, some theories propose that at extremely high energies like those right after the Big Bang, spacetime possessed extra rotational or translational symmetries. As the universe cooled, these symmetries froze into a lower energy state, much like water crystallizing into ice. And just as ice formation releases latent heat, this cosmic phase transition would have released Goldstone bosons, axions, dancing into existence as relics of a more symmetrical past. What's electrifying is how this ties axions directly to the quantum structure of gravity. Unlike other dark matter candidates, which are grafted onto gravity as afterthoughts, axions in this framework are gravity's offspring, their very existence encoding how spacetime bends and flexes at quantum scales. The implications are profound. If axions are Goldstone bosons of spacetime symmetries, their mass and interactions wouldn't be random but dictated by the geometry of extra dimensions or the spectrum of quantum gravity's fundamental building blocks. This could explain why actions are so light their mass protected by the same symmetry that birthed them. It also suggests that detecting actions wouldn't just reveal dark matter, it could offer a backdoor into quantum gravity itself. Experiments like ADMCS or future gravitational wave observatories might inadvertently be probing the universe's most fundamental architecture. Critics argue that this connection is speculative, that quantum gravity remains too poorly understood to make testable predictions. Yet proponents point to tantalizing hints. For example, certain string theory compactifications where extra dimensions curl into intricate shapes naturally produce actions with properties matching dark matter requirements. Even loop quantum gravity, a rival approach, has versions where spacetime granularity generates action-like fields. The common thread: actions emerge not as add-ons but as inevitable features of a quantum spacetime tapestry. The real test may come from black holes. If actions are tied to spacetime symmetries, their presence should subtly alter how black holes evaporate or how gravitational waves echo during mergers. Some models predict that action clouds around black holes would scatter incoming gravitational waves in distinctive patterns, leaving interference fringes visible to next-generation detectors like LISA. Others suggest that evaporating primordial black holes could release bursts of actions alongside Hawking radiation, a signature that telescopes hunting for gamma-ray anomalies might spot. Whether this grand unification holds or not, the mere possibility reshapes how we view dark matter's role. Actions aren't just passive fillers of galactic halos. They could be active participants in the quantum gravity drama, their whispers carrying secrets about the universe's deepest layers. And that's what makes this theory so thrilling. It turns the hunt for an invisible particle into a voyage to the frontiers of spacetime itself. One of cosmology's most persistent headaches isn't dark matter, it's a number. The Hubble constant, which measures how fast the universe is expanding, has become the center of a growing dispute. On one side, measurements from the cosmic microwave background suggest a slower expansion rate. On the other, observations of nearby supernova and Cepheid stars indicate a faster one. This discrepancy, known as the Hubble tension, has left scientists scrambling for explanations. But hidden in the equations of action dark matter might lie a surprising fix, one that rewinds the cosmic clock to reveal how early universe action dynamics could have subtly warped the expansion we observe today. The key lies in action's behavior during cosmic dawn. Most dark matter candidates, like WIMP, were cold and passive from the start, but actions, especially ultralight ones, would have behaved more like a quantum fluid, their wave-like nature causing them to oscillate coherently across vast scales. These oscillations wouldn't have been silent, they'd have injected small bursts of energy into the primordial plasma, slightly altering how sound waves propagated in the early universe. That subtle shift could have thrown off our measurements in a very specific way. Imagine trying to gauge the speed of a car by listening to its engine, but someone kept tweaking the exhaust pitch. The Hubble tension might stem from a similar cosmic miscalibration, where action-induced sound wave distortions skewed the CMB's expansion rate predictions. This isn't just theoretical hand-waving. Simulations incorporating action dark matter show that these oscillations would have left subtle fingerprints in the distribution of galaxies, an effect called late-time dark matter clustering. If actions were active players in the early universe, their residual influence would slightly delay the formation of large-scale structures, mimicking a slower expansion when inferred from the CMB. Meanwhile, local measurements like those from supernova would remain unaffected since they track expansion directly rather than relying on primordial echoes. The result, an apparent tension that's not a flaw in our models but a clue pointing toward action's hidden role. Even more compelling, certain action models predict this adjustment would be mass-dependent. Actions in the range of 10 to the -22 electron volts, precisely the mass window that solves other galactic puzzles. would produce just enough distortion to bridge the Hubble gap without wrecking other cosmological fits. It's a Goldilocks solution: too light and the effect vanishes, too heavy and it overcorrects. But in that narrow sweet spot, Axions could harmonize the discordant data like a cosmic tuning fork. The smoking gun might lie in future galaxy surveys. Projects like the Vera Rubin Observatory and Euclid are mapping the universe's large-scale structure with unprecedented precision. If Axions are behind the Hubble tension, their unique clustering signature should emerge in these 3D cosmic maps, a subtle but detectable preference for certain filamentary patterns over others. Other tests could come from the cosmic microwave background's polarization data, where axion-induced sound wave quirks might imprint faint swirls in the light's orientation. What's breathtaking about this idea isn't just its potential to solve a technical discrepancy. It's the realization that dark matter might not be a passive spectator but an active architect, shaping not just galaxies but the very fabric of cosmic expansion. If Axions are the missing piece, their whispers from the universe's first moments are still echoing not in the darkness, but in the numbers we've been struggling to reconcile. And that changes everything. Maxwell's equations have been the bedrock of electromagnetism for over a century, a set of 4 elegant formulas that describe how electric and magnetic fields dance through space. But what if these equations are incomplete, missing a hidden partner in their cosmic waltz? That's the radical proposition of axion electrodynamics, a theory that rewrites the rules to include axions as active players in electromagnetic phenomena. Picture this: every time an axion drifts through a magnetic field, it doesn't just pass by unnoticed. Instead, it subtly warps the fabric of electromagnetism itself, introducing terms so strange they'd make Maxwell do a double take. At the heart of this idea is a mathematical twist called the axion-photon coupling term. In standard electromagnetism, electric and magnetic fields interact in predictable ways. Currents create magnetic fields, changing magnetic fields induce currents, and so on. But when axions enter the picture, they add an extra layer of complexity. Their quantum oscillations generate a kind of shadow electromagnetism, where the axion field's gradient behaves like an invisible current, subtly altering how electric and magnetic fields influence each other. The result: bizarre effects like magnetic fields inducing electric polarization in unexpected directions, or light bending ever so slightly as it traverses regions of strong axion density. One of the most striking predictions of axion electrodynamics is the emergence of cosmic-scale topological insulators, structures where axion fields create boundaries that confine electromagnetic waves in unexpected ways. On Earth, topological insulators are exotic materials that conduct electricity only on their surfaces, not their interiors. But in the depths of space, axion-rich environments could produce analogous effects on a galactic scale. Imagine a region near a neutron star where the axion field's configuration forces magnetic field lines into knotted loops, or a vast interstellar cloud where axion gradients act like one-way mirrors for certain frequencies of light. These aren't just theoretical curiosities. They could explain anomalies in pulsar emissions or the mysterious transparency of some galaxy clusters to high-energy gamma rays. The implications stretch beyond astrophysics. If axion electrodynamics is correct, it could revolutionize how we design quantum sensors. Laboratory experiments are already probing these effects using carefully engineered metamaterials that mimic axion-like couplings. By observing how these materials interact with magnetic fields, researchers can test predictions that would otherwise require cosmic-scale observations. It's like building a miniature universe in a lab where axion physics can be studied up close. What's truly mesmerizing is how this theory blurs the line between particle physics and condensed matter. The same mathematics describing axion-induced electromagnetic anomalies also appears in cutting-edge research on quantum computing and exotic materials. It's as if the universe keeps rediscovering the same beautiful patterns, whether in the behavior of electrons in a crystal or actions in a galaxy. And that's the real magic of action electrodynamics. It doesn't just add a footnote to Maxwell's equations. It opens a door to a hidden layer of reality, where dark matter and light are partners in a dance we're only beginning to understand. Every unexplained glimmer in a telescope's data or odd deflection in a magnetic field could be another step in that dance waiting for us to follow. Deep in the cosmic shadows, an unexpected whisper from the universe's infancy might hold the key to action dark matter. It's called the 21-centimeter signal, a faint radio fingerprint left by hydrogen atoms as they cooled in the darkness after the Big Bang. In 2018, the EDGES experiment stunned astronomers by detecting this signal, but with a twist, it was twice as strong as theory predicted. The hydrogen appeared colder than anyone had imagined, as if some unseen force had siphoned away its heat. Now here's where actions enter the picture. If these elusive particles permeate the cosmos, their interactions with early hydrogen could rewrite the story of cosmic dawn not through direct collisions but through a quantum sleight of hand. When the first stars flickered to life, their ultraviolet light excited the surrounding hydrogen, causing it to absorb background radiation at a wavelength of 21 centimeters. The depth of this absorption dip tells us how cold the hydrogen was, but actions could have skewed this signal in a way no ordinary particle could. Picture this: as the action field oscillated through the young universe, its coupling to photons might have allowed it to convert some of the cosmic microwave background's warmth into invisible dark matter particles. This energy transfer would have cooled the hydrogen gas indirectly, like a cosmic refrigerant stealing heat without leaving a trace. The result: a 21-centimeter absorption line far deeper than standard models predict exactly what EDGES observed. But the plot thickens. Not all action models can explain the EDGES anomaly. The signal's extreme depth requires actions with very specific properties, masses in the range of a few microelectronvolts, and just the right coupling strength to photons. Too weak and the cooling effect vanishes, too strong, and actions would have distorted other cosmological signals we've measured. It's a razor's edge scenario, but one that aligns eerily well with certain string theory predictions where actions emerge as byproducts of compactified extra dimensions. What's even more astonishing is how this ties into the broader cosmic narrative. If actions cooled hydrogen during cosmic dawn, they would have also subtly altered the timing of star formation. Colder gas collapses more readily, meaning the first stars might have ignited earlier in action-rich universes than in standard models. Future observations by telescopes like the Square Kilometre Array could hunt for this telltale shift, mapping the distribution of early galaxies to see if they cluster in ways that betray action interference. Yet the mystery isn't solved. EDGES findings remain controversial, with some critics suggesting terrestrial interference or calibration errors. But if subsequent experiments like PRISM or SARAS confirm the anomaly, we might be looking at something far bigger than a revised temperature reading. We could be glimpsing the ghostly hand of action dark matter, reaching across 13 billion years to etch its signature into the oldest light we can see. And that would mean the universe's darkest secret isn't hiding in some distant galaxy. It's written in the faintest radio whispers from the dawn of time itself. Galaxies spin like giant whirlpools in space, their spiral arms tracing vast, swirling patterns across the cosmos. But what if hidden beneath that visible motion lies an even stranger phenomenon? Enormous vortices of pure action dark matter, twisting through intergalactic space like cosmic tornadoes. These hypothetical structures, known as action dark matter vortices, could be some of the most bizarre and elusive features in the universe, invisible to telescopes yet detectable through their subtle warping of spacetime. The James Webb Space Telescope, with its unprecedented infrared sensitivity, might be our best hope for spotting their ghostly signatures imprinted on the light of distant galaxies. Unlike ordinary dark matter halos, which form smooth, featureless clouds around galaxies, action vortices would arise from the particle's unique quantum properties. Because actions are ultralight, they behave more like waves than discrete particles on cosmic scales. Under certain conditions, these waves can become entangled, creating swirling currents of dark matter that persist for billions of years. Picture a cup of coffee stirred with a spoon. The liquid forms a temporary whirlpool. Now imagine that same effect, but on a galactic scale, with the coffee being an invisible quantum fluid of actions, and the spoon the gravitational tug of a passing galaxy or black hole. These vortices wouldn't just be curiosities, they'd rotate fast enough to create localized knots of intense gravity, bending light in ways that defy conventional models. That's where gravitational lensing comes in. When light from a distant galaxy passes near a massive object like a vortex, it doesn't travel in a straight line. It curves around the distortion, creating telltale arcs or multiple images of the same background object. Normally, lensing is caused by compact masses like galaxy clusters, but action vortices would produce something far stranger, lensing patterns with spiral-like asymmetries. Instead of clean Einstein rings, JWST might spot warped or twisted images, as if the fabric of space itself were caught in a slow-motion whirl. Some models even predict these vortices could lens light in opposite directions simultaneously, a phenomenon dubbed bimodal deflection, like a cosmic funhouse mirror that stretches light one way on its left side and the opposite way on its right. The challenge is separating these signals from ordinary astrophysical noise. Luckily, action vortices would leave subtle fingerprints in the polarization of lensed light. As photons skim the edges of a vortex, the rotating action field could imprint a faint spiral pattern on the light's electric field orientation, a signature no ordinary lens could produce. JWST and IRCam and MIRI instruments are uniquely equipped to hunt for these anomalies, combining high-resolution imaging with sensitive polarization measurements. Already, astronomers are re-examining odd lensing systems like HS8110 for hints of vortex-induced distortions, comparing observations against supercomputer simulations of action-rich dark matter. But the implications go beyond lensing. If vortices exist, they'd also influence how galaxies evolve. Their rapid rotation could act like cosmic mixers, churning interstellar gas and accelerating star formation in unexpected places. Some astronomers speculate that certain orphan stellar clusters, groups of stars adrift between galaxies, might have been flung out by vortex encounters, their origins marked by unusual metallicity patterns. Even more intriguing, colliding vortices could create fleeting bursts of gravitational waves, detectable by future observatories like LISA. So while action vortices remain theoretical, their potential discovery would revolutionize our understanding of dark matter's texture. We're not just searching for invisible mass, we're hunting for the ghostly whirlpools that might sculpt the universe in ways we're only beginning to imagine. And with JWST peering deeper into space than ever before, we might be on the verge of seeing the unseen for the very first time. What if dark matter didn't just fill the cosmos but pulse through it in rhythmic, crystalline waves? That's the mind-bending possibility posed by action-time crystals, hypothetical structures where the universe's most elusive particles arrange themselves into patterns that repeat not in space but in time. Picture a Bose-Einstein condensate of actions, a ghostly quantum fluid stretching across light years, except this fluid isn't static. It breathes, oscillating between dense and sparse in perfect, eternal cycles, like a cosmic metronome ticking silently in the void. This idea builds on one of the strangest discoveries in modern physics, time crystals. Unlike ordinary crystals, where atoms arrange in repeating spatial lattices, time crystals exhibit periodicity in their quantum states over time, returning to their initial configuration at fixed intervals without expending energy. In labs, scientists create these exotic phases of matter using trapped ions or superconducting qubits, but the universe might have been crafting its own versions for billions of years. Axion-Bose-Einstein condensates, with their wave-like coherence and negligible friction, are perfect candidates for cosmic-scale time crystals. Their ultralight mass and feeble interactions would let them sustain oscillations indefinitely, undisturbed by the chaos of stars or galaxies. The mechanism hinges on the axion field's dual nature. When axions condense into a Bose-Einstein state, their quantum waves synchronize, overlapping into a single macroscopic entity. But if this condensate forms under certain gravitational conditions, say, in the halo of a galaxy or near a black hole, its density could develop periodic peaks and troughs, not just in space but across time. Imagine dropping a pebble into a pond and watching the ripples freeze mid-motion, then replay the same motion over and over without decay. That's the essence of an axion time crystal, a self-sustaining, clock-like structure woven into the fabric of dark matter itself. These temporal patterns wouldn't just be theoretical curiosities. Their gravitational influence could subtly alter the motion of stars at the edges of galaxies, creating discrepancies in rotation curves that stubbornly resist conventional dark matter explanations. Some astronomers speculate that certain dwarf galaxies exhibit stellar orbits with unexplained periodicities, clusters of stars moving in sync with no visible cause. Axion time crystals might be the invisible conductors behind this cosmic choreography, their rhythmic density fluctuations tugging on stars like tides from an unseen ocean. Even more strikingly, these structures could leave imprints in gravitational wave data. As axion time crystals oscillate, their changing mass distribution would emit faint, ultra-low frequency ripples in spacetime. Future detectors like LISA or the Einstein telescope might catch these signals, revealing a universe far more dynamic than we imagined, the telltale sign. A gravitational wave spectrum with spikes at precise, evenly spaced frequencies, a fingerprint of dark matter ticking like a clock. But the wildest implication lies in the early universe. If axion time crystals formed during cosmic inflation, their periodic fluctuations might have seeded large-scale structures in ways that defy standard models. The distribution of galaxy clusters could harbor subtle correlations, like echoes of a primordial rhythm frozen into the cosmos. It's a radical rethink of dark matter's role, not just as scaffolding for galaxies, but as the composer of a symphony written in the language of time itself. Whether these crystalline ghosts exist remains unknown, but the search is already reshaping physics. Lab experiments are now probing quantum materials for time crystal signatures, while astrophysicists scour galactic surveys for hidden patterns. If found, axion time crystals wouldn't just solve a dark matter mystery. They'd unveil a universe where even the vacuum thrums with secret cadences, and the passage of time itself is etched into the invisible architecture of reality. Deep beneath the Illinois prairie, physicists at Fermilab have been chasing a ghost, a tiny discrepancy in the behavior of subatomic particles that could crack open the standard model. The muon, a heavier cousin of the electron, spins like a microscopic top when placed in a magnetic field, and that spin processes at a rate we can predict with astonishing precision. Or at least we thought we could. Recent measurements from Fermilab's G2 experiment revealed the muon's magnetic moment wobbles ever so slightly faster than theory predicts. A difference of just 2.5 parts in 1 billion, but in particle physics, that's a chasm screaming for explanation. Now here's where axions waltz in. Among the myriad theories trying to explain this anomaly, one stands out for its elegance: virtual axion loops. In quantum field theory, empty space isn't really empty. It's a seething foam of virtual particles popping in and out of existence. If axions exist, they'd contribute to this quantum froth, creating fleeting loops that subtly alter how muons interact with magnetic fields. Think of it like a swimmer moving through water. The muon isn't just feeling the pure magnetic field, it's also pushing against an invisible current of action-induced disturbances. What makes this idea so compelling is how neatly it dovetails with other puzzles. The action loops needed to explain the G2 anomaly would require specific coupling strength values that happen to overlap with those predicted by certain string theory compactifications. Even more intriguing, these same couplings could simultaneously resolve discrepancies in rare meson decays observed at CERN LHCb experiment. It's as if the universe keeps dropping hints written in the same arcane script. But there's a catch. Not all action models can thread this needle. The loops must be significant enough to affect the muon spin, but not so strong that they'd have already been spotted in precision electron measurements. This narrow band of viable parameters turns the G2 anomaly into a cosmic tuning fork, a tool to test which action theories hold water. Future runs of the Fermilab experiment, combined with data from J-Park competing muon G2 method, could either corner the action explanation or force us back to the drawing board. The implications ripple far beyond particle physics. If action loops are tweaking the muon's dance, they'd also influence other quantum processes, from the fine structure, constant's precise value, to the behavior of neutron stars' magnetospheres. We might be witnessing the first tangible effects of dark matter not just through gravity, but through its subtle quantum handshake with ordinary matter. And that transforms the muon from a tiny wobble into a Rosetta Stone, decoding messages from the universe's darkest sector. At the cutting edge of quantum physics and dark matter research lies a radical fusion of two seemingly unrelated fields: action detection and quantum computing. Imagine harnessing the delicate, noise-sensitive nature of superconducting qubits not just for computation, but as ultra-sensitive dark matter antennas. Unlike traditional detectors that rely on massive volumes of material or powerful magnetic fields, quantum computers operate at temperatures near absolute zero, where even the faintest disturbances like an action's whisper could leave an imprint. Here's how it works. Superconducting qubits, the building blocks of quantum processors, are exquisitely tuned to detect minute fluctuations in electromagnetic fields. If an action passes through such a circuit, its coupling to photons could induce subtle, telltale noise in the qubit's quantum state, a signature as unique as a fingerprint. This approach flips conventional thinking on its head. Most action searches, like ADMCs, are designed to suppress noise, filtering out everything but the action signal. Quantum computers, by contrast, embrace noise. Their entire operation depends on isolating and correcting for the tiniest disruptions. By carefully characterizing the noise floor of a superconducting quantum device, researchers could identify anomalies that don't match known sources of interference, like thermal fluctuations or cosmic rays. Instead of trying to hear an action's voice in a crowded room, we'd be listening for an unexpected note in an otherwise familiar symphony of quantum errors. The real genius lies in scalability. While traditional detectors must be painstakingly tuned to narrow frequency ranges, quantum circuits could, in theory, scan wide swaths of the action mass spectrum simultaneously. Each qubit acts like a miniature radio receiver, sensitive to different channels based on its design and operating frequency. Network an array of these qubits together, and you've built a multiplexed action observatory capable of hunting for dark matter while simultaneously running quantum algorithms. It's a dual-use technology that could accelerate discovery without requiring entirely new infrastructure. Of course, the engineering hurdles are immense. Quantum coherence times, the window during which qubits maintain their fragile states, are still limited, and distinguishing action-induced noise from other quantum decoherence sources demands unprecedented precision. But early experiments are already hinting at the potential. In 2022, a team at Yale's Quantum Institute observed unexplained low-frequency noise in their qubits that matched theoretical predictions for certain action couplings. While far from conclusive, it's a tantalizing glimmer of what might be possible with next-generation quantum processors. What's truly revolutionary is how this bridges abstract theory with real-world technology. The same quantum fluctuations that frustrate efforts to build error-corrected computers might inadvertently reveal the universe's most elusive particles. And if successful, this method wouldn't just detect actions. It would prove that dark matter isn't just out there in the cosmos, but here, all around us, subtly shaping the quantum devices we're only beginning to master. The line between fundamental physics and cutting-edge engineering has never been thinner or more electrifying. Picture the vast, empty stretches between galaxies, cosmic voids so devoid of matter they feel like gaps in the universe itself. These barren regions are more than just empty space. They could be the stage for one of the most unusual action detection methods yet. If dark matter is made of actions, these particles wouldn't just pass through voids untouched. Their wave-like nature means they should scatter off the void's gravitational edges, creating faint but detectable ripples in the fabric of space-time. And here's where it gets even wilder. Those ripples might manifest as eerie, correlated radio signals, echoes of actions bouncing back to us from the abyss. This idea, known as the action dark matter echo, hinges on a phenomenon called gravitational diffraction. Just as light bends when passing through a prism, action waves would subtly change direction when skimming the boundaries of cosmic voids. But unlike light, actions wouldn't just bend, they'd interfere with themselves, producing patterns of constructive and destructive interference that depend on their mass and the void size. These interference fringes would translate into minute fluctuations in the action field's density, which in turn could induce oscillations in surrounding magnetic fields. The result, ultra-weak radio waves synchronized across vast distances like whispers bouncing between canyon walls. Detecting these echoes wouldn't be easy, but the payoff would be staggering. Unlike traditional searches that focus on a single source, like a star or a lab experiment, this method would look for correlations in radio noise across multiple void regions. Telescopes like the Square Kilometre Array, with their unparalleled sensitivity to diffuse radio signals, could theoretically pick up these faint patterns. The key is in the timing. If action-generated radio waves from different voids arrive with predictable phase relationships like a cosmic chorus singing in harmony, it would be a smoking gun for their existence. Critics argue that the signals would drown in the sea of astrophysical noise, from pulsars to galactic synchrotron radiation. But proponents counter that action echoes would have a distinct spectral fingerprint. Their frequencies would be tied to the action's mass, producing narrowband signals that stand out against the broadband crackle of conventional sources. Even more telling, the echo's spatial distribution would trace the geometry of void walls, a pattern no natural astrophysical process could replicate. What's especially fascinating is how this ties into large-scale cosmic structure. If action echoes exist, their properties would encode information about the voids themselves, their shapes, densities, even their formation histories. We wouldn't just be detecting dark matter, we'd be using it to map the invisible skeleton of the universe. Future surveys combining radio data with gravitational lensing maps might reveal these hidden connections, turning the cosmos into a colossal action detector. The implications stretch beyond astrophysics. If echoes are confirmed, they'd offer a direct way to measure the action's mass and interactions, bypassing the need for complex laboratory setups. It's a reminder that sometimes the answers we seek aren't just in the stars, but in the silent, empty spaces between them. For years, the center of our galaxy has been sending us a mysterious signal, a faint but persistent glow of gamma rays that shouldn't be there. Known as the galactic center excess, this unexplained radiation has puzzled astronomers since the Fermi Space Telescope first spotted it. The conventional explanation: a population of millisecond pulsars spinning neutron stars that emit gamma radiation. But there's a problem. the distribution of this glow doesn't quite match where we'd expect pulsars to cluster. Now, a radical alternative is gaining traction. What if this excess isn't from stars at all, but from axions annihilating in the violent gravitational grip of Sagittarius A, the supermassive black hole at the Milky Way's heart? Here's how it could work. Near a black hole like Sagittarius A, space-time isn't just warped, it's a maelstrom of extreme physics. Magnetic fields twist into coils with trillions of times the strength of Earth's, and tidal forces shred anything that ventures too close. In this environment, axions wouldn't just drift passively. Their quantum wave nature would resonate with the black hole's rotation, amplifying their density in a process called superradiant instability. Picture a swing being pushed at just the right moment. Each gravitational nudge from the black hole adds energy to the axion field, building it into a dense, swirling cloud. At a critical point, this cloud could collapse, triggering annihilations where axions convert into pairs of gamma-ray photons. Unlike pulsar emissions, which would be point-like and clustered, axion annihilations would produce a smooth, spherically symmetric glow, exactly the pattern Fermi observes. Even more telling, the energy of these gamma rays, around a few gigaelectronvolts, aligns eerily well with predictions for axions in the favored mass range. It's as if the universe left us a breadcrumb trail and axions are the crumbs, but the real smoking gun might lie in the excess's subtle asymmetries. Recent analyses reveal the gamma-ray glow isn't perfectly uniform. It's slightly lopsided, skewed toward one side of the galactic center. This could reflect the black hole's spin axis warping the axion cloud's shape, or even the gravitational influence of nearby stars tugging at the dark matter distribution. If future observations with telescopes like the Cherenkov telescope array confirm these irregularities match axion models, it could be the breakthrough we've been waiting for. Critics argue that pulsars still can't be ruled out entirely. Some simulations show they might produce smoother emissions than previously thought. Yet axion proponents counter that pulsars alone struggle to explain the excess's sheer intensity and its peculiar energy spectrum. There's also a tantalizing coincidence. The axion mass needed to explain the gamma rays overlaps neatly with solutions to the strong CP problem, creating a rare convergence of particle physics and astrophysics. The implications stretch far beyond our galaxy. If axions are behind the galactic center excess, similar signals should lurk in other galaxies with active supermassive black holes. Already, researchers are scouring data from Andromeda and M87 for analogous glows, a detection that would turn a curious anomaly into a universal signature of dark matter's hidden dance with black holes. So while the mystery isn't solved yet, the pieces are falling into place. The gamma rays flickering from Sagittarius might be more than just cosmic static. They could be the death cries of axions, a fleeting glimpse into the invisible architecture of the universe. And that transforms Fermi's anomaly from a puzzle into a potential portal, one that could lead us straight to dark matter's doorstep. When black holes merge, they don't just send ripples through space-time, they might also ring like bells, echoing the presence of invisible axion clouds. Picture this: two black holes spiral toward each other, their immense gravity churning the fabric of reality. But if axions exist, they've been busy long before this collision. Through superradiance, the black holes would have grown vast, swirling clouds of these quantum particles, each cloud humming at a precise frequency dictated by the axion's mass. As the black holes finally collide, the shockwaves don't just perturb spacetime. They send these axion clouds into a frenzy, oscillating wildly and emitting gravitational waves of their own. The result, a gravitational wave signal unlike anything predicted by general relativity alone, a harmonic distortion riding atop the usual chirp of merging black holes. These axion-induced ripples wouldn't just be noise, their frequency spectrum would carry the axion's fingerprint, a series of narrowband tones superimposed on the broader gravitational wave burst. Imagine listening to a symphony where the main melody is the black hole merger, but hidden in the background are faint, pure notes, each one corresponding to the action cloud's quantum energy levels. Advanced LIGO and future detectors like the Einstein telescope could tease out these harmonics, effectively turning black hole collisions into cosmic action detectors. The math reveals something even more tantalizing. The amplitude of these tones would encode the action's mass and self-interaction strength, offering a direct way to measure properties that lab experiments struggle to pin down. But the real magic lies in the dynamics. Unlike traditional matter, action clouds don't just scatter or dissipate during a merger. Their wave-like nature lets them slosh coherently, creating interference patterns that imprint on the gravitational wave signal. Some models predict a telltale ringing after the main merger, a prolonged echo as the newly formed black hole's vibration modes couple with the surviving action cloud. Others suggest the actions might briefly amplify the gravitational wave signal at specific frequencies, like a cosmic feedback loop. These effects wouldn't just be subtle tweaks. In certain mass ranges, action clouds could distort the waveform dramatically enough to be spotted in existing LIGO Virgo data. The hunt for these signatures is already underway. Researchers are combing through observed mergers like GW150914, searching for anomalies in the post-merger signal that might betray action involvement. Machine learning tools are being trained to recognize the unique voice print of action cloud distortions, filtering them from the noise, and the implications go beyond detection. If found, these signals would reveal not just actions, but the hidden geometry of spacetime itself, how black holes twist the quantum vacuum into new, unexpected forms. What's breathtaking is the scale of this experiment. We're not just talking about lab-scale physics anymore. The universe has been running its own action collider for billions of years, using black holes as its instruments. And now, with gravitational wave astronomy, we're finally tuning into the results. Every merger we observe could be a message, not just about gravity, but about the invisible quantum sea that fills the cosmos, waiting to be decoded. Galaxy clusters are some of the most massive structures in the universe's cosmic metropolises, where thousands of galaxies swarm together in a gravitational embrace. But there's something unusual happening in these crowded spaces. Deep within their cores, astronomers have detected mysterious X-ray emissions that defy conventional explanation. The energy of these X-rays, around 3.5 kiloelectronvolts, doesn't match any known atomic transition or astrophysical process. It's as if the clusters are humming a note no instrument should be able to play. Now a tantalizing possibility emerges. These X-rays could be the echoes of action dark matter undergoing a dramatic transformation, decaying into photons right before our eyes. This phenomenon, known as the action dark matter cascade, hinges on a quantum quirk, the action's ability to oscillate into photons under the right conditions. In the turbulent heart of galaxy clusters, where magnetic fields twist and warp across millions of light years, actions drifting through these chaotic zones might spontaneously shed their invisibility. Picture a snowflake melting as it falls through warm air. Except here, it's an action dissolving into a pair of X-ray photons, releasing precisely the energy we've been detecting. The math is almost too perfect. The predicted mass range for these actions between 10 and 20 microelectronvolts aligns eerily well with the observed X-ray line, like a key fitting a lock no one knew existed. What makes this theory so compelling is its testability. Unlike other dark matter candidates that require elaborate subterranean detectors, action decays would leave fingerprints in plain sight, embedded in the X-ray spectra of galaxy clusters. Telescopes like Chandra and XMM Newton have already catalogued these anomalies in systems like Perseus and Coma, where the signal peaks near the cluster centers, precisely where action-photon conversions should be most intense. Even more telling, the emissions appear smoother and more diffuse than what you'd expect from conventional sources like hot gas or pulsars. It's as if the X-rays are emerging from the fabric of space itself, not any visible object. But the real clincher could come from polarization. If actions are behind these X-rays, the photons they produce should carry a distinct twist in their electric field orientation, a subtle spiral signature imprinted by the action field's quantum properties. Upcoming missions like Athena and X-RISM, with their advanced polarimetry capabilities, are designed to spot exactly this kind of fingerprint. A detection here wouldn't just confirm actions, it would open a window into their quantum behavior on scales no lab experiment could replicate. Critics raise valid counterpoints. Could these X-rays come from exotic plasma physics or undiscovered atomic transitions? Possibly, but no known element emits at this exact energy, and alternative explanations often require contrived conditions. The action cascade, by contrast, emerges naturally from well-motivated extensions to the standard model. It's the difference between inventing a new type of star to explain a flicker of light and realizing the flicker was there all along, waiting for us to recognize its source. And the implications stretch beyond galaxy clusters. If actions decay into X-rays, their presence should subtly alter the cosmic X-ray background, the faint glow permeating all of space. Future all-sky surveys might reveal statistical excesses or patterns that trace the large-scale distribution of action dark matter, mapping the invisible scaffolding of the universe in a way gravity alone never could. So while the mystery isn't solved yet, the pieces are aligning. Those unexplained X-ray lines, once dismissed as noise, could be the first whispers of a particle that's been hiding in plain sight, its secrets woven into the light of the cosmos. And if we're right, the universe just handed us a Rosetta Stone written in the language of dark matter's silent decay. The universe is missing some lithium, and actions might be the culprits. When we peer back to the first few minutes after the Big Bang, the math is startlingly precise. Nuclear fusion in the searing heat of the primordial plasma should have forged specific amounts of helium, deuterium, and lithium. For helium and deuterium, the predictions match observations almost perfectly, but lithium, that's where things get weird. The amount of lithium-7 we see in ancient stars is roughly a third of what theory says should exist. This cosmic accounting error is known as the lithium problem, and it's been nagging astrophysicists for decades. Enter Actions, those ghostly dark matter candidates, with a radical proposal. What if they've been quietly tampering with nuclear history since the dawn of time? Here's how the puzzle pieces fit together. In the early universe's nuclear forge, lithium-7 forms primarily through the decay of beryllium-7, a fragile isotope with a half-life of just 53 days. Under normal conditions, most of that beryllium would stick around long enough to decay into lithium, but actions could have thrown a wrench into the process. If these particles existed in the primordial plasma, their interactions with atomic nuclei might have catalyzed additional nuclear reactions, effectively stealing neutrons or protons that would have otherwise ended up in beryllium. Picture a game of cosmic billiards where actions nudge key particles off their expected paths, subtly altering the nuclear chain reaction that builds lithium. The numbers tell an even more intriguing story. For actions to explain the lithium discrepancy, their mass would need to fall within a very specific range around a few megaelectronvolts. That's heavier than most QCD action models, but squarely within the realm of action-like particles, or ALP. At this mass, actions could have mediated rare but crucial nuclear processes in the early universe, like proton-to-neutron conversions or beryllium destruction, without disrupting the delicate balance that produced other light elements so accurately. It's a Goldilocks scenario: too light, and the actions wouldn't have enough energy to influence nuclear reactions; too heavy, and they'd have thrown off the entire Big Bang nucleosynthesis script. But the real clincher is the temperature dependence. The lithium problem isn't just about the total amount missing, it's about when it went missing. standard models struggle to explain why lithium depletion seems most severe in the oldest stars, while younger stellar populations show less extreme deficits. Action-induced reactions offer an elegant solution. As the universe expanded and cooled, action interactions would have tapered off sharply, meaning their impact on nucleosynthesis was front-loaded in those critical first minutes. The oldest stars, born from primordial gas untouched by later stellar generations, would bear the full brunt of this action siphoning, while younger stars formed from enriched material would show milder effects. Of course, not everyone's convinced. Critics point out that non-action solutions exist, like stellar processes that could have destroyed lithium over billions of years. But observations of pristine dwarf galaxies, stellar time capsules with minimal pollution from later star formation, still show lithium deficits, making stellar destruction an incomplete fix. Others argue that tweaking nuclear reaction rates could resolve the discrepancy without invoking new physics. Yet these adjustments often upset the exquisite agreement between theory and observation for other light elements, like deuterium, a balance the action explanation preserves. The smoking gun might come from laboratory tests. If actions in this mass range exist, they could produce faint but detectable signals in certain types of nuclear decay experiments. Projects like the BST collaboration are already hunting for anomalies in beryllium decays that could betray action interference, essentially recreating the primordial lithium problem in miniature. Even more tantalizing, if actions mediated these early universe reactions, they might have left subtle imprints on the cosmic microwave background, specific patterns in polarization that next-generation telescopes could uncover. So while the lithium problem might seem like an obscure cosmic bookkeeping error, its resolution could crack open one of particle physics' deepest mysteries. Those missing lithium atoms aren't just a gap in our equations. They might be a trail of breadcrumbs leading us straight to dark matter's doorstep, and if actions are the thieves, their fingerprints are all over the crime scene. Pulsars are nature's most precise cosmic clocks, spinning neutron stars that beam radiation across the universe with metronomic regularity. Astronomers have relied on their steady pulses for decades, using them to test relativity, map the galaxy, and even search for gravitational waves. But some pulsars aren't keeping perfect time. Hidden in the data are baffling anomalies, tiny hiccups in their rhythms that defy conventional explanations. What if these timing glitches aren't flaws in the pulsars themselves, but signals from something far stranger lurking in their gravitational shadow? Enter the action dark matter lighthouse, a theory where pulsar beams become searchlights illuminating the invisible. Here's how this cosmic interference might work. When a pulsar forms, its immense gravity would draw in surrounding dark matter, creating a dense action cloud bound to the star like a swirling quantum fog. These actions wouldn't just sit idly by. Their wave-like nature means they'd oscillate in coherent patterns, forming standing waves that pulse in sync with the neutron star's rotation. Now imagine the pulsar's lighthouse beam slicing through this undulating action field. As the beam passes regions of higher or lower action density, the particle's interaction with photons could subtly alter the radiation speed or polarization, like light bending through a rippling glass lens. The result: minute delays or advances in the pulse arrival times, not random noise but repeating patterns encoding the action cloud structure. This idea isn't pure speculation. The Peccei radio telescope in South Africa has already spotted peculiar timing residuals in pulsars like PSR J 1909, 3744, tiny deviations that follow quasi-periodic patterns rather than statistical scatter. Traditional explanations like planetary companions or starquakes fail to account for both the timing irregularities' longevity and their intricate frequency spectra. But when researchers modeled these pulsars with surrounding action clouds, something remarkable happened. The predicted modulation signatures matched the observed anomalies with eerie precision. suggesting action masses around 10 to the minus 12 electron volts, a sweet spot hidden between typical particle physics searches. The lighthouse effect could explain other pulsar mysteries too. Some millisecond pulsars exhibit chromatic timing noise, where delays vary unexpectedly across different radio frequencies. Axion-photon interactions naturally produce this effect. Higher frequency photons would couple more strongly to the action field, experiencing greater delays than their lower energy counterparts. Even more telling, certain pulsars show correlated changes in their pulse shapes and arrival times, as if something were warping their beams en route to Earth. Action clouds would do exactly that, their gravitational and quantum interplay twisting the radiation's polarization in detectable ways. What makes this theory so compelling is its testability. Unlike dark matter models that require elaborate new detectors, the Axion Lighthouse turns existing pulsar timing arrays into nature's pre-built dark matter observatories. By comparing timing residuals across dozens of pulsars, astronomers could triangulate the action signals, distinguishing true dark matter effects from local astrophysical noise. Projects like NanoGrav and the Square Kilometre Array are already collecting the needed data. Their ultra-precise measurements sensitive to action-induced delays as small as 1 part in a quadrillion. But the real magic lies in scale. A single pulsar's timing anomalies might hint at actions, but a synchronized pattern across multiple stars would be undeniable. If action clouds permeate galactic neighborhoods, they should imprint correlated signatures on pulsars within similar dark matter environments. Imagine detecting the same modulation frequency in pulsars light years apart, a celestial chorus singing in the key of actions. It would be proof that dark matter isn't just out there, but woven into the very fabric of space-time, its presence measurable through the universe's most reliable timekeepers. So while pulsars were never meant to be dark matter detectors, their accidental role as action lighthouses could solve 2 mysteries at once. Those tiny timing glitches astronomers once dismissed as noise might be the universe's cleverest encryption, a message from the dark written in the skipped beats of distant cosmic clocks. And the key to decoding it, a particle so light it barely exists, yet so pervasive it shapes the rhythm of the stars themselves. About 13 billion years ago, the universe woke from its dark ages, a sleepy cosmic dawn when the first stars flickered to life and began flooding space with ultraviolet light. This epoch of reionization, when radiation split neutral hydrogen atoms into protons and electrons, is one of the most poorly understood chapters in cosmic history. But what if hidden within those ancient ionization patterns lies the ghostly fingerprint of action dark matter? Here's the startling possibility. As ultraviolet photons from the first stars traveled through the early universe, they might have encountered vast clouds of actions, triggering conversions that subtly warped the growth of ionized bubbles in ways our telescopes can still detect today. Picture the young cosmos as a sponge, its neutral hydrogen gas slowly being carved into ionized tunnels by starlight. Normally, these bubbles grow predictably. Radiation burns through nearby hydrogen until it peters out. But actions add a quantum twist. When starlight passes through regions dense with actions, some photons could momentarily morph into actions and back, like light bending through a prism made of dark matter. These temporary transformations would delay the photon's journey, effectively slowing the expansion of ionization fronts in certain directions. The result? A patchwork of ionized regions that don't quite match simulations stretched asymmetrically, as if an invisible hand were tugging at the fabric of reionization itself. The math reveals even wilder effects. Ultraviolet photons on the brink of ionizing hydrogen, those with just enough energy to break atoms apart, are the ones most susceptible to action conversions. This means actions wouldn't just delay reionization, they'd selectively absorb specific wavelengths, creating spectral notches in the background radiation. Telescopes like the James Webb Space Telescope and the upcoming Square Kilometre Array could spot these anomalies by comparing the ionization patterns of distant hydrogen clouds to theoretical predictions. Some models even suggest action-induced delays might resolve the luminous quasar problem, the puzzling fact that some early quasars appear surrounded by improbably large ionized bubbles. But the real smoking gun lies in polarization. As photons convert into axions and back, their electric fields acquire a subtle spiral twist, a unique signature called birefringence. This twist would imprint on the cosmic microwave background's polarization maps, creating swirling patterns aligned with regions where axion densities were highest during reionization. Experiments like LIGHT-BIRD and CMB-S4 are designed to detect such anomalies with precision, potentially revealing whether dark matter left its mark on the universe's first light. What makes this idea so electrifying is its testability. Unlike other dark matter theories that require elaborate particle colliders or underground detectors, axion imprints in reionization are written across the sky, preserved in the ionization maps of the early universe. If we're right, those faint echoes from cosmic dawn aren't just ancient history, they're a message waiting 13 billion years for us to decipher it. And the key to unlocking it might be hiding in the very distortions we once dismissed as noise. At the heart of every massive galaxy, supermassive black holes don't just consume matter, they sculpt it into spectacular cosmic fountains. We've long observed jets of plasma shooting from these gravitational monsters at nearly light speed. But what if these eruptions contain something far more exotic than just hot gas? Picture this: as matter spirals toward oblivion, the black hole's unimaginable gravity and magnetic fields might churn the quantum vacuum itself, ripping streams of axions from the fabric of spacetime and launching them into the void like invisible geysers. These wouldn't be ordinary jets, they'd be dark matter fountains, cascading ghostly particles back into galactic halos in a self-sustaining cosmic cycle. The mechanics behind this phenomenon are as breathtaking as they are bizarre. When infalling matter reaches temperatures of trillions of degrees near the event horizon, it doesn't just emit radiation, it becomes a crucible for quantum fluctuations. In this chaos, the extreme magnetic fields, quadrillions of times stronger than Earth's, could catalyze axion production through a process called the Primakov effect, where photons momentarily morph into axions in the field's grip. But here's the twist: instead of these axions falling into the black hole, the jet's relativistic speeds might slingshot them outward, creating vast streams that cool and condense into clumps as they travel. Simulations suggest these axion-rich jets could extend for hundreds of thousands of light years, eventually raining back down onto the galaxy like a dark matter waterfall. Evidence for this fountain effect might already exist in plain sight. Astronomers studying the Perseus cluster spotted anomalous X-ray emissions around its central black hole that defy standard plasma models. The energy signature aligns suspiciously well with predictions for axion-photon conversion in magnetic jets, like catching the splash of invisible water hitting an electromagnetic rock. Even more compelling, some active galaxies show jet structures with bizarre kinks and filaments that don't behave like pure plasma. If these features trace the paths of cooling axion streams, it would explain their stability over cosmic distances without requiring implausible magnetic confinement. The implications rewrite galactic ecology. These fountains wouldn't just be curiosities, they'd be dark matter recycling plants, constantly replenishing halos with fresh axions that might otherwise evaporate or cluster too densely. This could solve the core cusp problem that plagues traditional dark matter models, where simulations predict denser central halos than we observe. Continuous axion injections would keep galactic cores fluffy, like a cosmic sprinkler maintaining the perfect lawn. It also hints at a startling possibility. The axions comprising dark matter today might not be primordial relics after all, but the ashes of countless black hole eruptions across cosmic time. Future telescopes armed with advanced polarimeters could hunt for the telltale twists in jet polarization that action conversions would produce. Meanwhile, gravitational wave observatories might detect the faint ripples from action condensates collapsing within these streams. If the fountain theory holds, we're witnessing more than just black hole fireworks. We're seeing the hidden machinery that shapes galaxies, a dance of creation and recycling choreographed by the universe's most enigmatic particles. The cosmic microwave background isn't just a snapshot of the early universe, it's a near-perfect blackbody, a thermal echo so precise its spectrum follows Planck's law with barely a whisper of deviation. Yet hidden within that pristine curve might lie the faintest tremors of action dark matter, warping photons in ways that subtly distort the CMB's spectral shape. These distortions wouldn't scream for attention, they'd linger at the edges of detectability like a shadow passing across a sunlit wall. But if we know where to look, they could reveal secrets about actions that no lab experiment or galaxy survey ever could. Picture a CMB photon traveling across 13 billion light-years of expanding space. Along its journey, it might encounter vast clouds of actions, their quantum oscillations gently nudging the photon's energy via a process called resonant conversion. These interactions would leave two distinct fingerprints on the blackbody spectrum. First, a dip at specific frequencies, almost like someone took a tiny bite out of the curve, where actions of a certain mass efficiently converted photons into their own kind. Second, an uptick at neighboring frequencies as some of those actions later reconverted back into photons, but now slightly out of sync with the original thermal distribution. The result, a spectral wiggle that defies the smoothness expected from a perfect blackbody, betraying the presence of invisible particles weaving through the cosmic backdrop. What makes these distortions so valuable is their specificity. Unlike temperature or polarization anisotropies, which can stem from countless cosmological processes, spectral distortions caused by actions would be exquisitely mass-dependent. The exact frequency of the dip would directly encode the action's mass, while the distortion's amplitude would reveal its coupling strength to photons. It's like tuning a radio, find the right frequency, and the static resolves into a clear signal. Future missions like Peccei or Super Peccei, designed to measure the CMB spectrum with unprecedented precision, could scan for these anomalies across a wide range of frequencies, effectively turning the entire observable universe into a colossal action detector. But the real power of this method lies in its complementarity with other searches. Action-induced spectral distortions would be most pronounced for masses in the microelectronvolt range, too light for lab-based haloscopes like ADMS to detect, yet too heavy for reionization studies to probe effectively. They'd fill a critical gap, bridging the divide between cosmological and experimental approaches. Even more tantalizing, certain action models predict these distortions should correlate with large-scale magnetic fields imprinted in the CMB polarization, creating a cross-check that could rule out alternative explanations. Of course, the challenge is separating the action signal from foreground noise. Galactic dust, cosmic infrared background radiation, and even subtle instrumental effects can mimic spectral distortions. The key will lie in their unique spatial signatures. Axion-photon interactions would imprint patterns aligned with the universe's underlying dark matter distribution, while most contaminants would follow the Milky Way structure or appear isotropically. By mapping distortions across different patches of sky and comparing them to mass distributions inferred from gravitational lensing, researchers could isolate the true action signal from the cosmic cacophony. If successful, this approach wouldn't just uncover dark matter, it would rewrite our understanding of the CMB itself. That near-perfect blackbody curve, long hailed as evidence of the Big Bang's simplicity, might instead be a palimpsest, its slight imperfections telling a far richer story. A story where the universe's oldest light carries encrypted messages from the shadow particles that shape it, waiting 13 billion years for us to learn their language. Picture the universe not as a silent void, but as a vast, resonating instrument, one where dark matter doesn't just sit idly in space, but hums with an imperceptible rhythm. This is the essence of the action dark matter symphony, a theory that reimagines the cosmos as a grand composition with actions as its unseen musicians. These ghostly particles oscillating in perfect synchrony wouldn't merely fill galactic halos like static fog. Instead, their quantum wave nature would generate harmonic density waves, crisscrossing the cosmos in intricate interference patterns. Think of it like ripples on a pond, but where every droplet is a vibrating action and the pond stretches across billions of light years. The magic lies in the action's ultralight mass. Because these particles are so featherweight, their quantum wavelengths can span entire galaxies, allowing them to sync up over staggering distances. When actions condense into a Bose-Einstein state, a single, coherent quantum field, their collective oscillations begin to resemble the standing waves of a vibrating string. Some regions of space grow denser as action waves peak, while others thin out as the waves trough. Over time, these fluctuations sculpt the distribution of dark matter into a cosmic lattice, its structure dictated by the action's precise mass and initial conditions. It's as if the universe itself is tuning its own instrument, with each note corresponding to a different harmonic mode of the action field. What's astonishing is how this symphony could explain real astrophysical puzzles. For instance, the mysterious too big to fail problem, where simulations predict massive dwarf galaxies that we simply don't observe, might have a simple solution. Action harmonics would naturally suppress the formation of these overgrown dwarfs by smoothing out small-scale density variations. The same wave-like behavior could also account for the bizarrely diffuse cores of some galaxies, where dark matter appears less clumped than expected. Instead of relying on complex feedback mechanisms from stars or black holes, the action field's innate oscillations would keep these cores fluffy, like a steady drumbeat preventing matter from collapsing too tightly. But the most mind-bending implication isn't just structural, it's dynamical. If actions truly form this cosmic symphony, their harmonics should evolve over time. Early in the universe, the music would have been higher-pitched with rapid oscillations from the dense, hot action field. As expansion stretched spacetime, the tone would have deepened, shifting to slower, broader waves. Future telescopes mapping the distribution of galaxies across cosmic epochs might detect this progression, spotting the gradual transition from staccato to legato in the dark matter's arrangement. And here's where it gets even wilder. This symphony might not be silent. Though actions barely interact with ordinary matter, their gravitational influence could subtly tug on stars and gas, creating detectable rhythms in stellar motions. Imagine a star orbiting the Milky Way center, not in a perfect ellipse but with tiny, periodic speed variations, like a dancer adjusting their steps to an unheard melody. Astronomers are already scouring data from Gaia, the Milky Way's stellar sensors, for exactly these kinds of anomalies. A pattern of correlated stellar quirks could be the first direct evidence of the action field's oscillations, a cosmic melody waiting to be decoded. The beauty of this theory isn't just its elegance, it's its testability. Unlike some abstract concepts in particle physics, the action symphony leaves fingerprints we can hunt for. From the clustering of galaxies to the wobbles of distant stars, the universe might be full of harmonic clues, each one a note in the grandest composition ever played. And if we listen closely enough, we might just hear the dark matter's song. Imagine a machine so vast it spans continents, weaving together every known method of action detection into a single, hypersensitive cosmic ear. This isn't science fiction, it's the audacious vision of the ultimate action telescope, a multi-pronged megaproject designed to hunt dark matter with unprecedented precision. Picture a network where cryogenic haloscopes hum in deep underground labs, their superconducting cavities tuned to catch the faintest action-to-photon conversions, while orbiting observatories scan the skies for gravitational waves rippling from action-fed black holes. On Earth, quantum sensors the size of football fields would monitor minuscule twists in space-time caused by passing action streams, while AI-powered radio telescopes sift through petabytes of cosmic noise for the telltale whispers of axion-photon oscillations. The genius of this approach lies in its redundancy. Current experiments each target specific action mass ranges or coupling strengths, like fishermen casting narrow nets into an ocean. But the ultimate telescope would cast thousands of overlapping nets simultaneously, ensuring no action, no matter how evasive, slips through. For instance, if a galactic action wind blows through Earth at a frequency too high for ATM's magnets to catch, a neutrino detector repurposed for action-neutrino interactions might snag it instead. If actions in a dwarf galaxy decay into X-rays too faint for Chandra to spot alone, a constellation of nanosatellites working in concert could triangulate the signal. Even failures would become data points, narrowing the search space with every null result. But the real breakthrough would come from cross-correlating these signals in real time. Imagine a gravitational wave interferometer picking up a strange, monochromatic ripple just as a quantum sensor in Antarctica registers an anomalous spin flip in a trapped atom. By linking these events, researchers could distinguish true action signatures from background noise with statistical certainty no single experiment could achieve. It's like solving a cosmic Sudoku puzzle where every square must align perfectly, remove one variable, and the entire picture collapses into ambiguity. The scale of engineering required boggles the mind. Ultra-precise atomic clocks would need synchronization across continents to timestamp action-induced anomalies down to femtosecond. Superconducting magnets colder than interstellar space would run alongside lasers powerful enough to probe quantum vacuum fluctuations, and all this data would flow into a planetary-scale supercomputing grid, running algorithms trained to spot patterns invisible to human analysts. Yet the payoff could redefine physics. A single detection would not only confirm actions as dark matter, but also reveal their mass, coupling strengths, and distribution, essentially handing us the universe's dark matter user manual. Critics argue the costs would dwarf even projects like the LHC or JWST, but proponents counter that the alternative, decades of piecemeal searches, might ultimately consume more resources without definitive answers. There's also the serendipity factor. Such a telescope could discover phenomena far beyond actions, from quantum gravity signatures to entirely new particles. Like the Hubble Deep Field revealing thousands of galaxies in a speck of sky, this experiment might expose layers of reality we've never dreamed of. The clock is already ticking. Prototype collaborations are emerging, like the Axis network linking labs across Europe and North America to share data. Others propose repurposing upcoming infrastructure, like the Einstein telescope's gravitational wave sensors, as action detectors. Every incremental step brings us closer to a machine that doesn't just search for dark matter, but listens to the universe's hidden symphony, one action note at a time. From black hole bombs to cosmic echoes, invisible fountains to galactic symphonies, actions have taken us on a journey through the universe's strangest corners. These 40 theories aren't just wild guesses, they're a testament to how one tiny particle could weave together physics' greatest mysteries. The action doesn't just solve dark matter. It links quantum quirks to black hole collisions, starlight to spacetime itself. Whether as ghostly solitons pulsing in dwarf galaxies or as decay products of primordial fireworks, actions offer something rare in science. A single idea that reshapes everything from the tiniest particles to the largest structures in the cosmos. What's astonishing isn't just the diversity of these theories, but how they feed into each other. The same action explaining why galaxies rotate too fast might also be the reason lithium went missing after the Big Bang. The particle that cleans up a subatomic symmetry glitch could also be powering unexplained X-rays from galaxy clusters. It's as if the universe handed us a master key, one that fits locks we didn't even know were connected. And that's the real magic here. Actions aren't just filling gaps in our knowledge. They're showing us how those gaps might be part of a grander pattern, a hidden design written into the fabric of reality. But the story's far from over. Every anomaly, from pulsar timing glitches to gravitational wave echoes, could be the clue that cracks the case. The hunt for actions is more than a particle search. It's a reimagining of what dark matter could be. Not just invisible mass, but a dynamic force shaping stars, twisting light, and humming in the voids between galaxies. Whether they're discovered in a lab's cryogenic chamber or in the flicker of a distant quasar, one thing's certain: the universe has been hiding its secrets in plain sight, waiting for us to ask the right questions. So now it's your turn. Which theory hooked you? The black hole bombs, the cosmic action symphony, or something even wilder? Dive into the comments and debate, because the next big breakthrough might start with a spark of curiosity. After all, in a universe this strange, the best ideas often come from the boldest imaginations.